Good morning, everybody. So we start this morning session with the talk by Michael Shub about average of real roots and points of intersection.
Maybe I'll give a little bit of the history because I think it's kind of interesting. Steve Smale, proved the Poincare conjecture, all that 1960 or so. Then 1962 already, he's quite interested in dynamical systems, and he finds the horseshoe and sort of revolutionizes the subject of smooth dynamics. But by 1970 or so, I think he's already switching again. And now he's studying economics. And 1976, I was at a meeting at the CERM in south of France. The building wasn't built yet, I think. So we were all staying in Cassis. And there were there Herb Scarf from Yale and some guys from Princeton, and they were all talking about the fundamental theorem of welfare economics, which is that there is a price system that clears the markets, and that can be proven by using the Brouwer fixed point theorem on the right space. And Steve had a method using a kind of a Newton differential equation to find the zero or the fixed point. And Scarf and the Princeton people had various sort of simplicial approximations, and it was a very long meeting from my perspective. And I think after the meeting, Steve started to wonder, well, how do you compare? So now there's a question, if you've got various algorithms to solve a problem, how do you compare them? And I guess in numerical analysis, we didn't have a good theory. I mean, I shouldn't say we, there was no good theory. Theoretical computer science had a theory of complexity, but mathematics and numerical analysis didn't have such a thing. As far as I remember, there were normally libraries of problems, and then when you had an algorithm, you tested it out against the library and you published the results of how it did. And then you could argue with other people about what were the actual cases. And that was as I remember, the state of the theory at the time. So Steve started to think, well, I want to understand how to talk about comparing efficiency in numerical analysis. And so I think in the long term, he had the idea of trying to do something like theoretical computer science. But he started first with a classical solid problem that he thought he would investigate. And the problem was find the zero of a polynomial equation in one variable. So he started working on that around 1980, I think. And he came up with an algorithm. And I got involved in working with him on this subject fairly close to the beginning. And so here was what he did then. And I think the question in my mind, and I hope to explain it a little better, is still open. How do we really, what is a good method of comparing algorithms in numerical analysis? So here we start with one variable polynomial. Let me go over here in case I want to use the blackboard. So you start with one variable, and what he did is he took a point z0, and he looked at f of z0, and then you connected f of z0 with 0 by a straight line segment, and marked off points on that line, on that segment, trying to use Newton's method to solve for z1, z2 up to getting closer to 0. So that you might think of that as solving the equation f minus zi. So first you have f minus f of z0, and then you have f minus z1, which is, you might think a little bit later that you're really looking at the polynomial system, f minus t times f of z0. And now you're letting t go from 1 to 0, and that marches down. The root marches down this line segment, and you're just using Newton's method, getting an approximation to zk from an approximation to zk minus 1. And so then he proved the theorem. Well, this algorithm converges almost surely. And the average cost he expressed, I think he was pretty happy, he expressed in terms of the probability of failure. So he said the number of steps of Newton's method you have to take is less than 1 over, well, maybe it must have been a degree, a d over the probability of failure to the 7th power. Probability of failure to the 7th power. So I did point out to him that this algorithm, while looking polynomial, he's happy if sigma and sigma to the 7th is a polynomial, but it's infinite average cost, this polynomial. See, 1 over sigma 7th integrates to infinity, right? So there was a problem, and then we got working together, and we found out sort of various alterations to that method. We don't pick Z0, fix the first point. You may pick it at random on a circle of a given radius, and then it turns out that you do get finite averages, and I think this method is still being studied. The most recent results, I think, were by Myung-Hee Kim and Marco Martins and Scott Sutherland. And they give it's a fairly low degree polynomial by now in D. That is the number of steps that it takes on the average to find what's called an approximate zero. Smale also made clear what it meant to solve the problem, that he wanted to find a point where Newton's method is converging quadratically to a non-degenerate zero of the polynomial. So that was the problem. And then, so what did we do? After a while, we went on to systems. And we're going on to systems. There's a question here. See, somehow these polynomial systems that he was talking about had their coefficients in a polydisk. But that's, I don't know, it doesn't scale nicely. So from my perspective, this was not natural. So we went over, instead of looking at affine spaces of polynomials, to projective spaces of polynomials, just by considering homogeneous polynomials. So now, instead of thinking of affine polynomials, we have homogeneous polynomials, one more variable. Okay. And Renegar started studying this case of systems of polynomial equations, and he wrote this paper. It was too difficult. I mean, I couldn't read it. He was just really very, very good with making these estimates, and he's working in affine spaces. So he constantly had to divide by the norm of the vector to some power, and the formulas were complicated. But he did solve the problem and proved the theorem that with the probability of failure, the number of steps would be no more than 1 over the probability of failure to the 23rd power, I think he had at the time. So certainly not very practical. So we went over and we said, okay, homogeneous polynomials, roots are in projective space. Systems are in projective space of the space of homogeneous polynomials. And in that case, the roots are 0 on the complex line. If they're 0 at all, they're 0 on the whole line, because lambda pulls out as a factor. So you find a number of lines where the polynomial system is 0. So if it's a square system, which is what we're studying, we've got n polynomials, each of degree di, and n plus 1 variables, and they're homogeneous. And in that case, Bezout's theorem says that the number of roots is, when they're all isolated, the Bezout number, which is the product of the DIs. So you get system of polynomial of quadratic equations, say that's the most dramatic case. You have a system of quadratic polynomials and n variables. The number of roots is 2 to the n. The dimension of the space of systems is like little n cubed. So you have exponentially many roots of this system of polynomials, which is only little n cubed in its dimension. So this is a kind of a strange situation, I think, because you already, if you're looking for all the roots, you're in an exponential problem. But you might look for one root, and then it's not exponential problem anymore. And we attacked the problem by considering this variety V, which is contained in the product of the projective space of systems. Of course, the projective space where the roots lie, and it's the place where F is 0. So normally speaking, if you've got a system here, there are Bezout number, finite number of points in this fiber, which is exactly given by this Bezout formula, product of the DIs. This projection says the systems, the fiber, is the systems which are 0 at that point. So the systems which are 0 at a point are a vector subspace of the space of systems. So this fiber is a nice vector space, and this fiber is a complicated collection of product DI points. Some places it may have infinite degenerate zeros, but mostly it's got non-degenerate zeros and an exactly product DI of them. So this is the case where we're looking for elements of this fiber. And this picture, that's the complicated picture. But this picture is fairly simple. It's just a vector space. So what happens in a situation like this is that if you need to integrate a function, and I'm going to tell you a number of steps of Newton's method, maybe in terms of an integral. If I need to integrate a function, and I'm really interested in integrating here, well, I just pull it over here, and then I integrate it fiber by fiber over here over a linear space. So that's my strategy, and that's what we did. So now we say, okay, you want to solve a system, F0, well, you take an F0 where you know a root. So this is a point in V. Now we take the straight line to the one system you want to solve, and then you try to lift this path. And you lift the path by Newton's method, point by point. So I'm going to take, I increment the t a little bit, and then I try to find Newton's method. I have an approximation to this 0. I get an approximation to this 0 by using Newton's method, et cetera, until I get to the end. Well, that's the Newton's method. It's a little different here, sort of a projective Newton's method, where instead of inverting the derivative, we restrict the derivative to the orthogonal to the line. And then invert that. We have, after all, the derivative is taking n+1 space to n space. So I can't invert it, but I certainly need to. The inverse I could pick is the one with the least norm, which has got a name. It's called the, has all names now, and can't remember it. But it's, you pick that inverse, and you then use Newton's method. Oh, well, there should be an x minus or something here. X goes to x minus this. So, yeah, it's the wrong formula. Okay, but that's anyway, the projective Newton's method is essentially you take the tangent space to projective space, which is the orthogonal to the line. It's the natural Fubini-Studi candidate for the tangent space or projective space. And then you invert in that space, and then you push it back down into the nonlinear projective space. So that's Newton's method. And then you try to say, okay, how big a step can I take? That's the question. And normally speaking, the size of the step that you can take depends on this, how the norm of this inverse here. So if this is a very well-behaved map, you can take a pretty big step. But if it's not, you have to take a small step. If the norm of that map is big, you get outside of the, what would they call it? The distortion of the map, which is measures the nonlinearity. If the norm of the first derivative inverse is big, that space where you're close to being linear is generally smaller. And so if you're not close to being linear, then Newton's method is not quite so effective. And so you can't take such a big step. So the question is, as you come from here to here, and you're lifting, trying to lift this path, what is the integral of this norm of this operator along this path? So now here comes a few so here I actually say, what is the probability that this is large as you're moving across the path? And then what we have to do there is we got to look at that integral, which is in the face of it in the space of polynomials, but we're going to lift it up and push it down to the to this fiber. So how are we going to accomplish all this? Well, first of all, there's the question of what the let me see, did I even write it down here? Okay, well, I should at least mention the people involved. First, Smale and I did this in a series of papers, and we didn't quite solve the problem. We sort of gave an algorithm in the last paper that would do this in a polynomial number of steps on the average to find one root, to find k roots. It would be more like k squared times some number, but still very, very tractable, but we didn't have an actual algorithm. And then in various contexts, Beltran and Pardo, Borghese, Kuker, finally Pierre Lerez, who was then a student, solved the problem. So he, this was what Smale put it on his list of problems for the next century. This was problem 17, and Pierre actually solved it. And so there's a survey by Philippe Kuker that you could see about Smale's 17th problem. And then in one variable, Beltran and company, and maybe Carlos will speak about it in the next hour, have found a starting system. So when you have this polynomial, you want to find the system F0, and you want to connect it to any other system and try to follow the zeros along the path. And the question was what I call the finding hay in the haystack problem. Almost every system was good, but we didn't know a single one. So we had a high probability, if you chose a system at random, that it would be good for this process with one variable. But we didn't know a single example. It's like trying to find transcendental numbers. You say, okay, almost every number is transcendental, but name me some. So this is the hay in the haystack problem. And Beltran, I think, finally solved it recently. Okay, so there is a well-known starting point now. There was some conjectures ahead of time which are still open. So what's the proof here? Well, the proof relies on what the Hermitian structure is on the space. And so you put the natural Hermitian structure on that comes from Cn+1 and then scales properly. And that's just to divide the Hermitian product by the norm squared. And that gives you a well-defined thing on projective space. And then if you look at the two polynomials and you want to take their inner product, what you do is this is the normal inner product, which is just the coefficients times the complex conjugates of the coefficients of the other system. That's the normal inner product in Cn+1, but you divide it by d choose alpha. And that's because with this inner product, the Hermitian structure becomes invariant under unitary substitutions. So if I have f and zeta, such that f of zeta is 0, then f composed with u inverse is 0 at u zeta. So I have a action of the unitary group on the variety v, which takes a point f zeta to f composed with u inverse comma u zeta. So that's now the unitary group acting by isometries on the space. And that's absolutely crucial to the proof. So now we've got a Hermitian structure. So we can talk about volumes, we can talk about integrals, and we prove the theorem. So here's the action on V. So what we want to do initially is to take the question, well, I guess it's a long argument and I can't try to summarize it too easily now to go from there to integrating the inverse of the derivative along paths. But this is carried out in the sequence of papers we wrote at the time called Bezout's Theorem and Complexity 1 through 5. And then I added a sixth, which was helpful in this direction. So that's how the proof that we did and how these people have since resolved the problem, and Lorez has actually exhibited an algorithm which works in polynomial time on average to find a zero of a system of polynomial equations, n equations and n+1 unknowns, homogeneous. That's a polynomial time algorithm. It is a little interesting, I think, that this problem, knowing if a polynomial system has a zero, when there are more equations than variables, is an NP-complete problem in the theory of computation over the complex numbers or the reals or any field or ring. So the fact that you can actually find a zero in polynomial time in at least one context of the problem is a bit surprising, I might say. But it's done. So one morning, I guess I was visiting Berkeley, and we had a little house that we rented for a couple of months. I had this great job at IBM. They almost didn't make me have to go to work. So I was free to go visit universities, and I did quite a lot, and I spent some time in Berkeley, and there Steve and I were doing all this work, and we had all these integrals all set up. And so I decided that I would just see what it means for the reals. So I sort of said, let's write down the number of real roots to a real system. How many on average? So we know, I mean, like quadratic equations might have 0, 1, or 2 roots in the real numbers. So what's the average? How many roots does a quadratic equation have on average? So this is the question now, not only for quadratic equations, but for systems of equations, and putting it in the context of this double fibration. I'm trying to now integrate this function over PhD, but this is now reals, but the variety is the same. It's still a nice smooth variety. So I want to know the number of points in the fiber here. So I now lift this function here to a function that gives the same integral on V, and then I decompose it over here and try to integrate it here. So I have here the function number of points in the fiber. What I do here is put the function 1. Here I put the function 1, but I have to normalize by the Jacobian of the map. So I normalize, and then I do this one, and I have to now integrate over the fiber. So I have to normalize by the derivative in the normal direction here when I look at the fibers. And I take this integral, move it here, put it down there, and then I say the function is invariant under the orthogonal group. Now the orthogonal group preserves the same in a product structure. It's invariant on the orthogonal group, so it's constant in every fiber. Every fiber has the same number here, same integral. So I only have to integrate over one fiber. So now it makes my life easier. I've got one point, and I'm looking at all the quadratic or systems that have that point as a 0, and I want to integrate the number, whatever this integral is now, on that fiber. And I do that, and it only depends. So the fiber is now a linear space of systems. But the function I have to integrate over here, well, it started out with the Jacobian of this projection, and then there's the normal Jacobian of this projection, but they're all expressed in terms of the derivative of the system. So in fact, I was sitting there doing the computation, suddenly it reduces to linear algebra. And out comes, I have to, let me see if I remember this D choose alpha. So what is it? What if I had just a linear system, but now I'm thinking of it as the linear terms in some higher order polynomial, that I have to take the linear map and divide it by D choose alpha. But that's just D. Because all the degrees are 1. So I'm just going to, what am I trying to say here? The metric on the linear space is not the usual metric. It's the metric that's adjusted by this D choose alpha term, which is more or less D. So this change of variables pulls out of the integral. And the reals, it pulls out with a square root because it's only half the complex dimensions. So the square root of the product of the DI pulls out of the integral, and you're left with an integral that doesn't depend on the degrees anymore. And then since linear systems have one root, the average number is 1, and so produce the average number for real systems is the square root of the DI. So I must admit, when I finished that computation, which actually goes on for several pages if you write it down formally, I was thrilled. One of our friends came over and dropped by for a visit, and welcomed in the house and opened a bottle of champagne and celebrated. But then I must say that over the decades, I really haven't understood this theorem. I keep thinking, I've been thinking about it frequently, and I say, what makes this true? This is, the DIs pull out, and it seems like it has nothing to do with polynomial systems anymore. It only has to do with the metric. And, but what is the geometry here that makes this true? And I've just been stymied because there was too much structure here. There's the unitary group operating, there's the particular metric, there's the fact that you can decompose it in fibers. It's just too much. All right, so that's where I was. And I want to say a few things about it. One is that I think in doing this analysis, the condition number of the problem shows up. That is to say, the norm of the inverse of the derivative. So normally, that number shows up because it affects the precision in which you have to calculate in order to get an accurate answer. Right? The derivative tells you how much variance there is if you move the parameters a little. So if you just know your problem approximately, the derivative tells you the range of possible answers. And if that range is big, then you're in trouble. You have to compute with higher and higher precision to get an accurate answer. So that's the normal role that this number, the condition number, plays in numerical analysis. But here, it's not only playing that role, it's playing a role in the number of steps. The number of steps itself was an integral of this condition number. So the condition number enters into another way here. And in terms of the actual complexity of sort of the algebraic complexity, not just the precision complexity. So you might think that's maybe somehow natural, and I don't think the subject has been explored enough. I mean, certainly Grigorio Malajovic and I and Felipe Kuker have made up models in which the condition number is part of the input size, and now you're talking about things that can be solved in polynomial time, including the condition number. And so there's a little bit of a subject that's been developed there, but not a whole lot, I would say. And I think it deserves a lot more attention. In some sense, you could see in the type of problem we're talking about, the inverse function is analytic, but it's not analytic globally. It's going to have poles. So as you come closer to the boundary of where the analytic function converges, you could imagine that it takes you more arithmetic operations to evaluate it, because it's going to, the sum is infinite. So you stop at any finite point, you may not be large, might even be small. So the fact that the inverse system is not converging analytically might be an indication that you have to take into account something like the condition number of the system, at least in terms of, say, the distance to the boundary where the inverse is well defined. So this is a question of how the condition number plays a role. I think it's worth a lot of consideration, is because, of course, with rational maps, you have poles, but you don't have to do any more algebraic work. It's all there in the denominator. So, so it's not at all a clear issue. The other issue is where to start the homotopies. This was, I think it's still a good problem. There are some starting points now, or proven methods due to Lasserre mostly, and Lasserre and Kuker and Bergieser, but it's still lots of open questions as to where good starting points are. And the last thing that I think needs a lot of attention is this notion of average. So I'm saying to you, the average number of steps in Newton's method is this. What is a theory that incorporates average? What is its complexity theory? So for example, some of the people do averages. They do what they call, I think it's called Las Vegas. You have a probability of failure. You may even get the wrong answer. So then you ask, what is the number of steps in terms of this probability? So that you might have something polynomial in that, but you may get the wrong answer, and that may be so catastrophic that you don't want to use such a method. On the other hand, it'd be more expensive if you want to say, what is the average if I want insist on getting a correct answer on almost all cases? At least checkably at the end that you can verify that your answer is correct. So that's another type of average. How do all these compare? Is there a good complexity theory in the average case? And how do we compare average results? So I think we're almost back to where we started 40, 50 years ago. We still need to know how to compare our results, and theoretical computer science has such models. I think they do have an average case complexity. There's a one-page paper by Leonid Levin that talks about such a thing. It's too complicated for me, but I guess maybe computer scientists can understand it. Anyway, we have no theory about comparing the averages. Okay, so now what's the topological version? So the first question is, how can I replace the use of the unitary group? So what I'd like to be able to is compare any 2 points in the manifold locally. So what I ask for is a submanifold of diff. Now diff, if you look at diff M cross M, you have the evaluation map, Fm goes to F of M. This is a locally trivial fibration over M. So what I would really like to, and not only that, its derivatives of all orders are naturally surjective onto the relative jet bundles. So I'd like to have a submanifold, compact, finite dimensional submanifold of diff, which has some of those properties, like locally trivial fibration, or at least a submersion for every evaluation. And also I'd like it to surject nicely onto the derivative space, the jet bundles. So I ask, is there such a manifold with the following properties? And I'm kind of surprised I didn't find anything in the literature. I mean, if anyone knows something, please tell me. This must be an obvious fact, because here's this infinite dimensional object which has all these properties, and you want to sort of say, okay, let's start taking finite dimensional approximations of it. At some point, it's going to be a surjective derivative. So then by compactness, at some point, you'll get surjective derivative everywhere. So why not? This seems like it should be obvious. Well, Axel Kodad is working on it, and we want to have some of those properties where the map is a submersion. Maybe it has to be a manifold with boundary. So I think we can accomplish that. I hope we can find a manifold with boundary contained in diff, which has those properties. But it would be life would be much simpler if we actually had a compact manifold without boundary, and that would make life better. But I don't know such a theorem, and I don't know how to prove such a theorem. But anyway, I think we're finding such a submanifold, which is sort of diff, which is sort of like saying up to some kind of finite distortion, every manifold is a homogeneous space. It's not a group. I'm not saying it's a group action, this H, but it is a subset of diffeomorphisms, and it's comparing any, it's compact, and it's comparing any 2 points in the manifold. So, and then here's the theorem that there are constants. This is such that for any 2 complementary submanifolds of M, if you look at the number of points of intersection, and now you average that over your space H of diffeomorphisms, that is comparable to the product of the volumes of the 2 submanifolds. And I put no conditions on the submanifold. They're compact. So for example, these could be disks of complementary dimension. And in fact, well, the proof of the theorem is the same as the square root of D. You set up this variety V, which is the you look at the number of points, you take out the derivatives, you look at the quotients of derivatives, you prove that's bounded, and then you get these bounds K1 and K2. So that's, and in fact, the theorem's true, they don't have to be complementary dimension. So you take any 2 manifolds, and you look at their intersection, normally speaking, they'll be transversal and you'll get a submanifold. And this submanifold will have a volume. And now you integrate, in the case that the submanifold is 0-dimensional, the volume is the number of points. But if the manifolds are not 0-dimensional, you actually get an intersection. Then you get a volume of that intersection, and it's the same theorem. The average volume of the intersection is up to a constant. It doesn't depend on anything but that space H, the volume of V times the volume of W. I don't have a lower bound there. I had a lower bound in the other thing. I'm not sure about the lower bound. But so this is work in progress. It's mostly Axel Kodats, who is home in New York writing proofs, which I hope are correct. I think they are. Anyway, so that's what I have to say, and the method of proof is the same here. It's written down, and somewhere in our book we have a general theorem about how to count the number of points of intersection, and then in the case where it's not points but volumes, you have to adjust that theorem a little bit. But it's all in terms of the derivatives of this sort of local solution maps. Okay, thank you. Sorry about the confusion with
Well, that's that's not serious. Any questions, anybody?
So the H, the
yeah.
submanifold of diff-M or whatever that comes with a volume form. I mean, what are you averaging? What are you using to do the average there?
Oh yeah, whatever volume form you want on H. It's a compact manifold with boundary, but pick one.
Oh, just anything.
Anything.
Does it have to be? It doesn't even have to be like supported on all of H, or
oh. Yeah,
just
I
non-degenerate.
make it a Riemannian volume.
Okay.
Pick a Riemannian metric and smooth Riemannian metric. All these things can be C infinity. The submanifolds V and W don't have to be. They might be C1. But H should be built in the context of C infinity maps.
And they should have handed me the mic. I have another question. So for really high degree systems, I mean, it's not even clear to me that a zero is practically meaningful in a lot of circumstances. Is there a notion of like a meaningful zero? Because I mean, you'll have a lot of zeros and they might be close to each other. And
yeah, so the zeros we're talking about, Smale defined the notion where the zero that he's looking for is an approximate zero, he calls it, where means that Newton's method is actually converging quadratically on that point to a zero. So you can get the distance to be log epsilon with, I mean, to be epsilon with log epsilon terms. So even for a high degree, if log is reasonably small compared to whatever you're dealing with, then this approximate zero is a good notion, I think, and it's testable. So here you can verify that a point is an approximate zero just from data at that point. So you have to compute maybe the derivative and the first few higher derivatives, and then you could assert, yes, this is an approximate zero just from the computation.
it's actually tracking a zero and only one zero at that point.
Yes.
Yeah. Yeah. Okay. Thanks.
Yeah, I have questions. So yeah, so the average estimate that you get very good is yeah, in theory is very good. But I concerned about the practical aspects. So I know that, for example, this method is used in the Bettini software, but I don't know if you or your co-author, so did you try to really practically compare your method to other methods? Like, for example, there's a well-known method in solving system equation called the
Yeah.
Levenberg-Marquardt. So I don't know if you did you compare practically? I mean,
Yeah.
practically, not
I
theoretically.
hardly know how to turn my machine on, as you saw today. So I don't do any programming. I don't even, you can see this is all handwritten. I don't even type mathematics. So I certainly don't program any algorithms, and I don't do that type of test. But maybe almost certainly Hauenstein does, and he may speak about questions like that. I'm mostly interested in theory myself, and I have an application for this theorem in mind, but it's still another theorem. It's nothing practical.
I was wondering to which point the use of Newton's method is essential in your theory. Could you choose another way to progress in your homotopical method? And because
Yeah,
I see that you obtained very good bounds, but another issue in numerical analysis is precisely to invert linear systems.
so from this perspective, I think back in probably around the early 1980s, Smale and I studied not only Newton's method, but Taylor series method. So you could take a higher expansion and then you try to use that to approximate the curve better. So you have higher order methods besides Newton's method. What we found, and then when my student Myung-Hee Kim studied this relation, because it's true that if you use a higher order method, you can go further in the parameter. But on the other hand, it costs more for each step. So what she found at the time was that for one variable, Newton's method was cheapest to achieve the number of steps you need, except for a fourth order method that she found. So there was one method that was roughly comparable in efficiency to Newton's method. And but the other methods, the higher order methods, actually were more expensive.
I was actually thinking to lower order method, like, I don't know, gradient methods or fixed point methods, because if we increase the problem in size, these are at this day the only method that are tractable.
Yeah. So the question is, what's a good stopping value? If you're not, Newton's method has this guaranteed convergence, which is quadratic, which lets you get small epsilon with a few steps. But with gradient method, you'd have to, you slow down as you come. You have to do some kind of speed up to get.
So you use this famous Smale theorem to say that that's okay. You are near the point you wanted to approximate.
Yes, yes, we can actually give an estimate of how far you are from the point. There is, I think, there was a problem. Is there a generally convergent algorithm that Smale raised at some moment? And McMullen's thesis proved that there isn't in the complexes. So that he used the theory of rational maps to prove that you could not have, in degree 6 or bigger, I think, some method that you put in the coefficients of almost every equation would spit out an approximate root. So you can't have that, but you can with sort of gradient type, even little speeded up methods. So Smale and I proved that if you could add in the fact that you could compute the modulus of a number, then you could have generally convergent algorithms. Polynomials, I don't think they were as fast in the tail, but maybe they were at some point. It was either Newton's method and you switched over to a gradient method, or I don't remember, but it was in the mid 80s sometime.
Any more questions?
Thank you.
Okay, the second talk of the morning session will be by Carlos Beltran about starting points for the homotopy method to solve systems of equations. Please.
Yes, thank you. So, well, first, thank you very much for the invitation, and thanks to all of you for being there. And I'm sorry that I cannot be physically with you there. And thanks for maintaining the invitation despite the circumstances. So, well, part of this talk will probably repeat a bit some of the contents of the previous one, but there will also be quite a good deal of new stuff. So let me start by making some graphical description of some of the concepts that have appeared in the talk by Shub. One of them is the condition number of a polynomial, or more generally, the condition number of any numerical problem that you can conceive probably. In most numerical problems, you have a space of inputs, which is the space where the inputs can live, right? It could be the space of polynomials. It could be the space of systems of polynomials. It could be the space of problems of linear optimization with a fixed number of unknowns and a fixed number of equations. It could be many things. It could be the space of PDEs of a certain type. Then the space of solutions, the space where solutions live. Well, in this case, you have the input spaces polynomials, then the space where the solution lives is the complex numbers, or the complex projective, if you talk about homogeneous polynomials, right? But it can be anything. So if you're talking about real linear optimization, then the space of solutions will be R to some power. Or if you're talking about solving PDEs, then the space of solutions will be the space of functions of a certain Sobolev type, say. Usually these spaces have a structure. They can be vector spaces of finite or infinite dimension. They could be manifolds. And you can always consider this object that I call here the solution variety. solution variety is just a set of pairs, input, comma, its output. Of course, an input can have several outputs. Yes, like it's a space of polynomials. In case of polynomials, they have several outputs, right? Several roots. So this manifold that I kind of picture there, it could turn among itself and have several solutions for a given input, right? Now, in this is the setting that Shub and Ismail in the 90s used for defining the condition number, and that gives a general geometric setting for the classical notion of condition number. So probably most of you know that the first definition of condition number is due to Turing and von Neumann. Maybe there is a bit of a dispute who exactly invented it, but well, that's not very relevant, right? The thing is that they define the condition number of a matrix as a number that will measure how much the solution will change of a linear system when you change the matrix. So AX equals B, you change A a bit, how much does X change? So this is very meaningful towards application. That's quite clear. And well, that's an algebraic definition. If you put this in this setting, so if you say the set of inputs is the set of matrices, you fix B, for example, and you say the set of outputs is the set of Rn, which is where X lives. And then this manifold would be the A comma X such that AX equals B. Then you define the condition number with the formula that I'm going to show, and you get Turing's condition number. So that is a general geometric setting for the condition number that includes sensible definitions of the condition numbers to the date. Now, this object is many times a manifold. Many times just an algebraic variety. In the case of polynomials, in the case of systems of polynomials even, this is a manifold, which is called V in Michael's talk. Now, here is the definition of the condition number. Formal definition of the condition number is the one that you find up there. So you take any pair, input comma output, say FC, and then you can consider pi1 and pi2, the two projections at this point. Now, if the solution is properly defined, say, isolated, then you're probably lucky enough as to be able to guarantee that pi1 can be locally inverted. If pi1 can be locally inverted, then you can consider this object there, the derivative of pi1 inverse, then the derivative of pi2, to compose them. And this is a linear operator and has an operator norm. This operator norm is the geometric definition of the condition number. Now, if you think about it for 1 minute, you see that this exactly is telling you how much will the solution change when you change the input just a bit, right? So it's a local version of this intuition. Change, you shake the input and you see how much the output changes. And then, well, this is a reasonable definition, right? So essentially, well, apart of having the formula, which is quite a clear geometric concept, you can just take this one-line idea that is sketched below, like large condition number is equivalent to the zero is not stable. In the meaning, what does it mean? That small changes in the input imply large changes in the output. So the slide is written for polynomials and zeros, but same slide, changing notation holds for systems of polynomials and zeros in C to the n, or zeros in some projective, complex projective, or real projective, or matrices as inputs and x's as outputs. So the idea is quite general. Here is written for polynomials. Now, in the 90s, Shub and Ismail started studying and putting the foundations of what is nowadays the standard theory of homotopy for solving polynomial systems of equations. And well, they use this method of homotopy that I will talk a bit about in a few minutes, and that Mike sketched. And essentially, after thinking about it, which they came to this question here. So they kind of thought, if we are wondering about following a path to see how the zero moves from one system to another, then we are certainly very unhappy if the zero suddenly changes a lot. So we would be interested in systems or in polynomials whose zeros are quite stable. But then can we find one? So this is the problem of high in the high stack that Mike mentioned. Why high in the high stack? Well, they proved that for a random polynomial or even a random system, the expected value of the condition number is quite slow, quite small. But it turns out to be quite difficult to find one single polynomial with a small condition number. Why is that? Well, essentially because the standard choices that you would make are not valid, like roots of unity. Well, roots of unity polynomial, its condition number is super polynomial. It's like 2 to the power of a square root of the degree or something like that. And any other choice that you try, say from a naive point of view, or at least any naive choice that people have tried, have not produced an answer to this question. So can one find a polynomial such that the condition number is smaller than the degree? With the knowledge that there exist a lot of polynomials such that the condition number is smaller than the degree. So that is the question by Shub. Now, let me mention a bit again about homotopy. I wrote here a slide for the homotopy method, and I wrote it for the polynomial eigenvalue problem. Instead of for the system or polynomial problem, I wrote it for the polynomial eigenvalue problem. Why? Because it's possible. Because you can use homotopy for many numerical methods. One of them is here. Here is the sketch. The sketch is the same. So you will have an input matrix A whose eigenvalues and eigenvectors are not known. And then you would choose a matrix with known eigenpairs. For example, a diagonal matrix. Then you would join them in the space of matrices, and you would try to follow these solution paths, these information paths. Now, there have been several questions about the method to use, right? It's true that from the theoretical point of view, the most usual way to solve this problem is using Newton's method. Why is that? Well, you can just write an ordinary differential equation system for how the solution moves. So if you write AT lambda t equals lambda t vt with t a parameter, and you compute the derivative with respect to time, you quite easily get an ODE that the solution path will satisfy. Why don't you just apply Runge-Kutta or something like that? You can do that. Yes, this kind of works in many cases. But there are some problems, and one of them is that you have, in general, many solution paths, right? Like if you follow systems or you follow solutions to polynomials or to eigenvalues, you have many paths. And if you're not very careful, it's quite easy that you jump from one path to another. That's a problem because you lose control. And when you lose control, you cannot prove theorems, right? So that is a powerful reason to use Newton's method. The fact that you can guarantee the convergence is a guarantee to have a method that does not jump from one path to another. And this means that you can make expected values and things and so on, thinking that all paths are equally probable and things like that. Now, if you have jumps, you don't have that anymore. So that is one strong reason for that. Now, actually, the problem for computing eigenvalues and eigenvectors is solved by machines since at least 40 or 50 years ago very efficiently, and everybody knows that. But James Dennell in the 80s, he wrote a question. He said, okay, after so many years of very good service by the QR method and the different variations, say QR with Francis shift, probably the most popular right now, or in the last years. After all of that, we don't have a proof of global convergence, which says it is fast. So our proof is that it works. Our proof is that planes fly, ships go from one place to another, and that you put it in MATLAB and you put the enter and it works very well. But we don't have a proof of that. So that he said, and this problem was open until 2014 or so on, when with Armentano, Diego Armentano, Peter Burgisser, Felipe Cocura, and Michael Shub, we proved that one could get a definite complexity estimate, which is average polynomial time, using the homotopy method. So one powerful thing of the homotopy method is that it allows you to prove theorems. And well, this does not mean that the method is practical. Actually, I don't think anyone would be using the homotopy method to solve the eigenvalue problem right now. Maybe at some little steps, but not the homotopy method itself, for sure. Even from the theoretical point of view, after we published that, this has been improved. There's this work by Banks, Garza Vargas, Kulkami, and Srivastava, introducing holomorphic functional calculus, very interesting work in foundations of computational mathematics, that actually they are able to also prove a theorem of expected number of arithmetic operations to solve the eigenvalue eigenvector problem with a different thing, which is not homotopy. And they get a better complexity estimate. Right? But well, the power of homotopy is that this can be used in many different contexts. Now, let me switch back to the problem of finding a polynomial such that its condition number is small. Actually, the way that Mike and Steve came to that question was, let me go back a bit to here, was thinking about this homotopy. They proved, and Mike mentioned that the number of steps, of Newton steps that you needed to do this task of going from known system or known polynomial or known matrix to the input one, the number of steps depends on the condition number on the path. This is supernatural, because if the path is varies very wildly, then you will certainly have to make a lot of steps in order to follow it closely. Right? Now, yeah, this is natural idea, but it is not easy to put it to work. Right? So it is not until complexity of method number 6 in the 2008 by Mike that we get the current version now, which is a very, very strong version, which essentially says that the number of steps that you need to follow the path is the length of the path in the condition metric, which is the metric in this solution manifold multiplied by the condition. So essentially, large condition, small steps, and then longer time, right? Then Mike and Steve say, okay, if we are going to solve problems by homotopy, we need two things. We need a method to follow paths, and we need a starting point. So the starting point, Mike mentioned a bit about that already, and I will talk more. And this was quite a long-standing problem. And in the 93, they thought the following way: okay, if condition number is bad, we are certainly, if large condition number is bad, we are certainly not going to start in a polynomial whose condition number is large, because we would be like starting bad from the beginning, right? So why don't we start a polynomial or a system of polynomials whose condition number is small? This is not a proof that the thing will work, right? This is just a reasonable idea. But the problem was posed there. And then, as I say, well, it is not easy to find a polynomial whose condition number is small. Now, I will talk about that problem now for a while. We think of polynomials. Actually, we think of homogeneous polynomials whose zeros are hence in the complex projective space, P of C2. Now, P of C2 is has one model, which is the Riemann sphere. That is the sphere over x 1/2. And then you can think on a polynomial, you can think of its zeros as a complex projective points, and you can think of these zeros as points in the Riemann sphere. And this way, you can identify polynomials with points in the Riemann sphere, and you can think about, instead of having a good, well-distributed polynomial Can I think about having well-distributed points in the Riemann sphere or in the sphere? Can I do that? Right. So that is a way that Mike and Steve came to the problem that I mentioned. Let's change a bit our point of view now and think about points in the sphere. Let's distribute points in the sphere. So this is quite a popular way to do this, the way that I put in this slide. Compute the log energy of these points. What is the log energy? Well, this here. It's just sum of the log of 1 over the distances, mutual distances, just that. Of course, you can write it as 1 over the product of the mutual distances, log of that. Yes. Then if this is very, if you have 2 points which are very close, then the corresponding term in the summation will explode and you will have infinity. So if this is minimized, you won't have very close points. It will be quite well separated. That's a version of classical Coulomb potential right here. So actually this problem without the log was posed by Thomson, the discoverer of the electron and the Nobel Prize winner in 1903 or 1904. He was thinking about this model of atomic, model of atom where it was a positive ball with little negative charges that would be the electrons, and he was asking how will they distribute. So this problem, he posed it, but then the quantum mechanics came and the model of the atom was not correct, and then this question quite somehow fell into oblivion. But it was recalled later and later again, and it gained a lot of importance in different applications that I can mention later if you wish. So that's a way to decide how well some number of points is distributed in the sphere, right? Small energy, well distributed. Big energy, not well distributed. There are other options, I insist. You can remove the log, and you get what you call Coulomb potential. You can say sum of 1 over the squared distances. This is called Newton potential. But you can say sum of 1 over the distances to some power. Let it be s, some little s. So that would be called the Riest potentials. These are all different problems, somehow related ones to each others, but different. Other options would be to say, okay, instead of minimizing sum of 1 over the distances, let's say maximize sum of the distances, or maximize sum of the distances to some power. And these are all related yet different problems. So the one that I choose here is important towards the study of complexity and condition, and also towards other things. So this leads to 2 deep questions in approximation theory. One of them is here. So what is the minimum value of the energy? So if I tell you, let's say that you take 2 points in the sphere, what is the minimum value of the energy? Then you will immediately say, okay, they must be opposite, and then the value of the energy is like a log of 1 over 2, or like minus 2 log 2. Okay, perfect. Now, if I give you n points, what is the minimum value of the energy? That's there. Well, one option would be to look at this other question. Like, okay, you want to know the minimum value of the energy? Don't worry. I will generate the points that have the minimal value and then compute their energy. Yes, but this is a very difficult question. Very difficult. This was posed by Mike and Steve. Nowadays, it is known as a Snell's 7th problem because it came into the list of Snell's problems for the 21st century. But I insist that there are 2 different questions, because this first question here, what is the minimum value of the energy? We know a lot of things about it without generating the points. While this question here is probably very far from being solved. Now, I insist that Shub and Snell came to this problem, starting from the complexity and from the condition of polynomials. And we will come to this. Now, let me give you a few clues about what happens if you just try to generate points in the sphere in different fashions. Here is the conjecture for the minimal value of the energy. The minimum possible value of the energy is conjectured to be this thing. So you have a certain constant times n squared. This constant has a meaning. It is the expected value of the energy of 2 points. You let 2 points at random in the sphere, you let them be at random, you compute their expected log energy of these 2 points, and you get this number, 1/2 minus log 2. Then you have this term here, and then it is known that there is a constant times n, and it is not known what happens later. And the value of the constant is not known. The value of the constant is conjectured to be a certain number. It has a formula, gamma of 1/3, blah, blah, blah. It's conjectured to be a certain number, and it's known to be smaller than that number. So the conjecture is that it is equal. The theorem by Beltran and Sandias is that it is smaller than or equal to this. And the lower bound, last lower bound by Lauritsen for C log, is almost the same. It's minus 0.056. So meaning that there is a 0.001 place where nobody knows where the constant lives. Everybody thinks it is the value here. Now, what happens if you take some collections of points in the sphere? You have to think that choosing collections of points gives you polynomials directly, right? Take these points in the sphere to the Riemann sphere, then to the projective, then consider the monic polynomial with these zeros, homogeneous polynomial. And then you de-homogenize it if you wish. So points in the sphere implies polynomial. What happens if you take just n random points in the sphere? So I wrote here the minimum possible value. Just this is the thing that I wrote before. Well, this is the conjecture, I insist. There is an unknown thing here, so we don't know if this is a 5 or a 6. Random points, if you see this, you get the correct number in the n square. That is quite reasonable, having into account that this number came from choosing 2 points at random in the sphere. But random points do not get this n log n. So of course, you cannot just choose random points in the sphere and expect that they are well distributed. So this is a more sophisticated ensemble by Krishnapur, the spherical ensemble. So this is a way of choosing points in the sphere which has a randomness. It is called a determinantal point process. And the easiest way to think about that is here. So you take A and B matrices whose entries are normal 0, 1 complex. Then you invert the first one, you multiply by the second one, and you compute the eigenvalues. These eigenvalues live in the complex space. Just send them by the stereographic projection to the Riemann sphere, and you get collections of points like this one. And it turns out that the energy again has the correct n squared term, and now it has the correct n log n term. Of course, it does not reach the correct n term, but at least you gained quite something. That's the spherical ensemble. And this computation was made by Alisashi and Famani after studying Krishnapur's ensemble. Here's another way of thinking about it. Well, we started wanting to have a well-distributed polynomial, a well-conditioned polynomial. Then we said, okay, let's look for well-distributed zeros, but well-distributed zeros is very difficult. So why don't we choose a random polynomial and then solve it? Because we know that random polynomials are well conditioned by Shub and Snell's theorem. So this question, we made it with Diego Armentano and Mike Shub in 2008, in the maybe last 2 weeks of my stay there with Mike in Toronto, the University of Toronto, that Diego was visiting us too. And then we were able to compute it exactly, the energy of zeros of random polynomials. So this is Armentano, myself, and Shub. And we get the correct n squared term, the correct n log n term, and not the correct, but better n term than previously known sequences. So let me go back to Krishna-Purse ensemble, you get 0.4, and we got 0.19. So this was for some time the collection of random points whose energy was proved to be the least possible. It's a bit disappointing. Why? Well, because Smel's seventh problem says that you want points whose energy is log n close to the minimum. Now, the original problem was finding a polynomial whose condition is small. Now, if random polynomial condition is small, but random polynomial, the energy is certainly not log n close to the minimum, then this means that, that the problem of distributing points in the sphere must be much harder than the problem of finding a well-distributed, well-conditioned polynomial. Well, this can be good or it can be bad, right? It can be bad, meaning that you won't be able to solve the sphere problem as easily, but it can be good by meaning that you might be able to solve the polynomial problem easily. Now, there are other popular choices of points if you look in the literature. Here is one. This is called the Rachmaninov-Sartsou spiral points, and there are many other collections of points, many others. So there are papers, survey papers, very nice, with different collections of points, their energy, their other distribution properties, a lot of them. There's one by Harding and Saf in the Dolomites journal, for example, that's very easy to read and very, very nicely written. And the spiral points, this is the way that they are constructed. Sometimes they are called Fibonacci points. The way to do it is you get the sphere, you start here down, and then you put the point and you move it up. Then you move a bit round, a bit up, a bit round, a bit up, a bit round, a bit up. This until you get up this sphere. Now, how much is a bit up, a bit round? Well, this has to be very carefully stated, very carefully computed in order to produce something which is reasonable. So they did that, which is not easy to do. And they got some sequence with very nice properties apparently, but nobody has been able to compute the energy of this kind of sequences. Now, recently with my students, Sucuetayo and Pedro Ramon Lopez Gomez, we introduced this thing which is called the diamond ensemble, which is a very, very naive idea, which is the following one. So if you want points in the sphere that are well distributed, why don't you choose the easiest option, which would be just take the two poles and choose a number of parallels. So parallel of height 0.9, parallel of height 0.7, and so on. And in each parallel, you put a number of points which are equispaced. Why not? See, and it's not so easy to prove, but it's true, is that if you let each of these parallels rotate by random phases, well, this will come later, you can actually compute the log energy. So that is a very infrequent property of concrete sequences of points. So, well, actually, in practice, if you choose the number of parallels, which is P, and if you choose how many points you put in each parallel, then the heights of the parallels, you don't have to choose them. You just check very easily that there is a unique optimal choice. And it all amounts then to choose how many points you put in each parallel. We describe the diamond ensemble by distributing them following first continuous and then not continuous linear piecewise function. And we get this. We get the value of the energy for this ensemble. Once these parameters are chosen in an appropriate way, gets the correct underscore term, the correct and log n term, and not the correct, but quite close to the n term. So let me recall that the correct term here is minus 0.055 or 56. So this means that we are only 0.0067 far from the conjecture minimum. Now, we started in polynomials and their condition. Change it to the sphere, Suddenly we have a set of points in the sphere that is easy to describe and easy to analyze. And the polynomial whose zeros correspond to these spherical points is easy to understand and easy to write down. So that is quite a good candidate for having a small condition number on the average. That's a claim. Actually, if there is a relation between condition number and log energy of the points, then expected condition number is small. Here is the log energy of expected zeros. If we get better log energy, we should be getting better conditioning too. Now, the relation of these concepts comes from a couple of sides, and one of them is this formula here that we discovered with Armentano and with Mike Shub. This formula relates the log energy of spherical points, which is an object from potential theory, with the condition number of a polynomial. So it turns out that the logarithm of the condition number of a polynomial at the different zeros, is sum of the zeros, is related to the log energy. And the relation comes from a third quantity, which is here. So maybe it's too much of a notation to introduce all of this, but if you are familiar to the Bombieri inequality or to the Weil norm of polynomials, this is the Weil norm of a polynomial. And this is the product of the Weil norms of the factors of this polynomial. So this is essentially product of the norms compared to norm of the product. Talking about Bombieri inequality and Weil polynomials, this has a meaning in number theory. And then this equality relates three fields of mathematics which were quite unrelated apparently at the beginning. Well, there is later a constant that only depends on the degree and is hence not very important or meaningful. Now the thing is that with this relation, another one that I will say later, one can actually use the knowledge that we got here with the diamond ensemble to produce knowledge here and knowledge here. Well, here's the name of the paper that we published with Huetaggio and Jordi Marzo and Kim Ortega Cerdán, which are two colleagues from the Universidad de Barcelona. Huetaggio was my PhD student. Is now here at the University of Cantabria. And later we improved it in some senses with other two students, Fátima Lizarte and Pedro Ramón López Gómez. And I summarized our result in this slide. So here's the thing. Let's start by the formula in the bottom. This formula was stated by Shub and Ismail in the 93. I said before, the condition number of a polynomial, well, a polynomial can be written in terms of spherical points, right? So if you work it out, you might expect to be able to write the condition number as a function that only depends on the spherical points. Yes, this can be done. So it takes you a couple of weeks or 3 weeks of computations. But if you are really convinced that you can do it, then you get to this expression here. So big N is the degree of the polynomial. And then the condition number of a polynomial is the constant of the degree. And here, the xi's are the zeros in the sphere. The zeros in the sphere of radio 1 corresponding to the zeros of the polynomial. Now, what you see here is exactly the quantity that comes into the log energy, but without the log. Remember that the log energy was also written as 1 over the product of the mutual distances, log of that. If you quit the log, you get this here. So this is e to the power of the log energy, the denominator. So this is second relation. Recall, this was the first relation, log energy, the sum of the logs. Now, it turns out that the maximum condition number, you have the exponential of the log energy. And what do you have here? Well, this is, P is just a point in the sphere. So this is a 2 norm. This is the 2 norm of a function that for any point gives you the distance to all the other points. Product of all this. This is a 2 norm. So you can expect that if number of points are well distributed in the sphere in the sense that this is small. They will also be having this small. Here we have the diamond ensemble that I told you before. So you see that in each parallel you have a number of points and so on, and they are quite reasonably chosen. Unfortunately for this, from this is not so easy to get to a polynomially bounded condition number. But with Jordi, Martin, Kim, Ortega, Ferrat, we had to make some transformations of this set, and we ended up by producing this other one, which is essentially obtained as follows. So you start from this diamond ensemble, and you consider the intermediate parallels. So between this and this, you can imagine an imaginary line which has no points. And then part of the points here and part of the points here must be sent to this intermediate one and must be rotated properly. And then you get to a set like this. And what we proved is this thing here. Well, here you get the number of points, and here is the condition number divided by a square root of n. Maybe this is not very clear. So you get that this is like 14, but later we improved it. This is the result that we have now, which is the lower bound and the upper bound for the best condition of polynomials, which is this lower bound and this upper bound. So you may remember that the problem posed by Micah and Steve was condition is smaller than the degree. So we get much better because we get square root of the degree. This lower bound, this is not sharp, but the reasons to think that this might be more or less like 0.5, around 0.5 will probably be the best concept. This is normal. Also, I must say that from this approach and using the three fields inequality that I mentioned before, Ujue Tallo was able to improve Bombieri inequality by an exponential factor in a paper in transactions. Now, this talk is about starting points of the homotopy. So let me come back to starting points of the homotopy, maybe recalling a bit something that Mike said, maybe saying some things more than that. Now, in the 90s, Mike and Steve founded this modern homotopy theory. And they posed this initial pair problem, which was, where do we start the homotopy? For polynomials, they posed the problem of, why don't you find a polynomial which is well conditioned? And for systems, they posed a particular conjecture, which they gave one particular system, which has one zero, which is very well conditioned, and all the other zeros are terribly conditioned. They asked, can you start at this system and find most likely very fast 1 0 of systems? Can you do that in polynomial time? This is still open. So with Luis Miguel Pardo, we proved that random initial system provides polynomial time complexity on average, and we gave a method to generate random initial systems. And this was called a randomized solution to Snell's 17th problem, which is the problem of proving average polynomial time for systems. So what we got is number of Newton steps, polynomial. Well, this little n is the number of unknowns, little d is the degree, big N is the input size. So here you have the code for that. Big N is the input size. So this is essentially order of big N, because big N, the input size in dense encoding is much bigger than these ones, right? So essentially O of n. Now, Burgisa and Cooker were able to remove the randomness hypothesis of the initial pair by choosing a system which was like the n-dimensional version of the roots of unity that was actually used in practicing in some programs, existing programs, but no one had been able to prove any complexity result. So they proved that taking that particular system, you could get quasi-polynomial running time. I'm sorry. Then Lasserre, in 2016, found a trick to avoid randomness initial pair, maintaining the polynomial time complexity. So here you have, we got like random O of n, deterministic, almost O of n, and Lasserre's proof deterministic O of n. Now with Armentano, with Peter Burgiser, Felipe Bucher, Mike Shub, Diego Armentano, we proved that the randomized version could be done faster, going down to the square root of the input size. And then in the 2020, Lasserre proved, oh, sorry, this N should not be here. Sorry, this should not be here. Lasserre proved with a slightly different, well, a different approach to homotopy, instead of based on linear homotopy, based on something he called rigid homotopy path, you could get number of steps polynomial in N and D without the big N. So this is state of the art up to 2020, starting by randomized O of N and finishing in randomized O of not N, only poly N. This is randomized, although Lasserre said, and he's right, that the trick to avoid randomness could also be done here. Now, the trick to avoid randomness is mainly a theoretical artifact, and it does not improve, say, like the practice of programming of the algorithms. But these rigid homotopy paths do improve the practice of programming. They do give a different way to program that I think would improve quite a lot the performance of actual methods. Now, there are improvements to this thing, and this will most likely be said by Peter in his talk, which is that all these rigid homotopy paths can be done better. They can do it even in structured systems, which has been a fundamental open question that started. Well, you can see the solution in Peter's talk. And I must say, well, this is all theory. Someone asked about practice before. So amazing results about solving systems with homotopy method exist in the literature. I would say that the work in the last years by Hauenstein and collaborators show, I mean, you can just install this Bertini software, alpha certified software in your system, and you will be able to solve very large systems very fast, really very fast. So practice goes way beyond the theory. Theory is already quite good, because the theory, without this N, which is a typo, the theory says that you only need to worry about a very little number of polynomial of Newton steps, very little number. It is quite unthinkable that one could prove the same kind of results for other things which are not Newton method, like say, no, do Runge-Kutta or do higher order, blah, blah, blah. I don't think it would be so easy to prove these modern results with other different methods, because they use very, very smartly the gamma theorem, Snell's gamma theorem, which is the key point of Newton method. But I insist the practice is way beyond theory. Practice is incredible. It's very, very fast, solving a lot of problems in practice. So I don't know, someone said before in the public, I don't know who, because I couldn't see, but someone said that for large systems, these homotopy methods were not so practicable. Well, I would say, listen to the talk by Hauenstein if he talks about that. They are practical methods that actually work super, super good. Now, if you look at all of this, all of this does not need a starting point which is well conditioned. Does not need it. This first solution, random system, no need to have it well conditioned. This other one, particular system which is not well conditioned. This other one, essentially random with a trick, not need of a well-conditioned initial system. This one, randomized, not need of initial well-conditioned system. This one, also not need, also not need, also not need. This has been working for 30 years, way before the well-conditioned polynomial was found. So there is no need, actually, now. And actually, as I said before, there was this kind of intuition, let's start in a well-conditioned point. But this was not a proof that this will work. Actually, the proof came by Peter and Felipe when they proved in 2011 that if you start at a point which is well-conditioned, then the complexity of homotopy will be polynomially bounded. With our result for polynomials, sorry. So now we have a well-conditioned polynomial to begin with. If we combine this with their result, what we get is this complexity for solving polynomials, not for systems. So this is crazy. It's really crazy. I mean, no one would be using a method for solving polynomials with this complexity. Actually, some of the randomized problems that I mentioned, algorithms that I mentioned before, already get better. And on top of that, no numerical analyst would probably use homotopy to solve polynomials. They will just construct the eigenvalues and solve it by QR with shifts and so on. No theory, but extremely good performance in practice in many cases. So what is the need of well-conditioned pairs to begin with? Well, that's a theoretical need, answering the question. And it also has this beautiful relation with the problem of distributing points in the sphere that is nowadays called Snell's problem. And well, here's another question. Later, before I mentioned this work by Diego Armentano, Peter Burisser, and Michael Shub, where we stated that one can use homotopy to solve the eigenvalue eigenvector case in polynomial running time, average polynomial running time. This was the first time that this was proved, even although practice much faster, much beyond. Okay, yes, but this was the first theoretical proof. Now, can we actually also solve the polynomial problem for the eigenvalue case? Namely, can we find a matrix whose eigenvalues are very well conditioned, all of them? So together with Armentano, Borghese, Cooker, and Shub, we already gave an answer which was positive. So choosing a certain diagonal matrix, you would get eigenvalues which are well distributed. Now, recently with Beltran, Grabner, and Steiner-Berger, we proved that we had an optimal choice, at least to first order. And this optimal choice is choosing the matrix which is diagonal and whose entries are the points in an hexagonal net. So this was also used in this paper before, but here we proved that this is optimal. You cannot do better than that up to first order. And I will finish this talk with this slide. Here you can see three different sets of points. This set of points was obtained numerically by getting points whose logarithmic energy is as small as possible. This one here was obtained by getting the zeros of a polynomial, asking the polynomial numerically to be as well conditioned as possible. And this head here is different. This comes from the set of points such that the corresponding polynomial satisfies an optimal Bombieri inequality, also numerically. All of these three cases can only be done numerically for this number, which is 20, if I remember. But if you can see them, I mean, you cannot distinguish them by just a sign. So there is this conjecture we made at some point, that is that this inequality here, minimizing this, maximizing this, might be equivalent problems, or equivalent up to some order, meaningful order. This is also an open question. So thank you very much for your attention. So I'll finish here.
Yeah, thank you for your interesting talk. So I just have a couple of questions. So first, for the energy, for the Coulomb generalized Coulomb problem. So what do people expect about the solution? Are they transcendental numbers or are they algebraic numbers?
Well, yeah, so I would say that people expect transcendental numbers because the conjecture here So the conjecture here for the C-log term, this is a transcendental number, the conjecture value, right? So this is expected to be certainly transcendental. Now about this, we don't know anything. So I don't know what people would expect. Optimistic people would expect that there is just a log n term here. This is not known.
Okay, so if the solutions will be transcendental numbers, so I think if you try to cook up some family of points, you won't never be able to get to the minimum, right? So maybe you need to do some iterative process, right?
Oh, now I see your question. Yes. Yes. So because I'm talking about asymptotics here, but you ask for a concrete number of points, right? To know if you would be able to find rational solutions. Actually, I have a paper about that where it's proved that if you have any solution to a small 17th problem, so it's small 7th problem, so any collection of points whose log energy is minimum, then if you move any of the points in a ball of order 1 over the number of points to the 3/2, then you only deviate 1 over a small constant, so 1 over 10 from the log energy minimum, meaning that maybe you cannot solve exactly, but with small rational numbers, you can get extremely close values to the logarithmic energy. Only with, say, like log n number of bits in the representation of rational numbers, you can get it. So actually, by an enumeration procedure, you can solve the problem. You just consider all the collections of rational points whose denominator in the sphere, whose denominator is of the size of n to the 3/2, and then one of them has the energy which is 1 over 10 close to the minimum, right? But for the exact solution, no, I don't think anything is known about it. I think that the exact solution is only known for number of points 1, 2, 3, 4, 5, 6. If you'd say which is the exact solution, the best log energy points for 7 points, this is not known. So essentially, we wouldn't have an answer for that.
Okay, yeah, thank you. So can I have one last question? So concerning your second part of the talk, so okay, so I understand that in for example, if you want to solve an equation, then usually the iterative methods like Newton method or gradient descent or whatever. So the role of the why you need to choose the random point at the beginning is that you want to avoid some exceptional case where your process will not converge to a solution but may converge to a critical point of the associated function. So I don't know in your homotopy theory. So so what's the role of if you want to choose some random points or random curves? Yeah.
So if you want to choose, for example, if I understand the question, you're given a polynomial and you want to choose, you want to take one random choice, one random root of that polynomial, right? Did I understand it correctly, or?
Yeah. So I mean that in the usual run in this iterative method. So the role of the random choice is that you want to apply. For example, you don't want to go to a startup point, or you don't want to go to all the critical points of the associated function, which are not solutions to your polynomial, for example. And so, but then in your method, homotopy method, you also need some kind of randoms, and I don't know if it's if they also have the same role, or you choose them randomly because of some other reasons.
Okay, I see. Yeah, no. Well, the randomized solution which I stated with Luis Miguel Pardo, and later we improved with Diego, Peter, Felipe, and Mike. This randomized is done because of two reasons. One of them, because it allows you to prove theorems, and it is not easy to prove theorems without the randomized option. And the second of them actually is that if you randomize the system, you have probability 0 of getting into trouble. I mean, that if you choose your system as random, then with probability 1, any input system will be solved. The question is that some input systems will take longer than others, but all of them will be solved except for a 0 measure amount of them, right? So you cannot go into, say, like it will happen to you with gradient flow. You cannot go into a local minimum and you stuck there, things like that. This will happen with probability 0. And moreover, we also proved that actually choosing this random system at random to begin with, if you look at the probability distribution of which 0 are you solving of a given input system, the probability distribution says that all of them are equiprobable. So that is like an extra advantage that you would get from there. I think that that's all that I can say regarding your question. I don't think that I have.
So I have kind of a vague theoretical question here, and that is that when you're trying to find like energy minimizing distributions of large numbers of points, I mean, points that are far apart shouldn't really count for much in the energy. So is there some way, if you just keep track of all the points within distance, let me make something up, say 1 over square root of n, and use that as a kind of easier substitute for the energy, is it provable that, you know, minimizing that is really, really close to minimizing the energy? Does that make any sense the way I'm asking it?
Oh, yeah, it makes a lot of sense. And this is quite an open question. If you, for example, if you choose points with the property that they are maximally separated, like in the sphere, you can set the collection of points whose mutual distances is the less mutual distance is as large as possible. Does this solve the energy problem? This is not known. Actually, one of the very few concrete results with concrete numbers is precisely for that problem. The exact separation is known. I mean, if you put n points in the sphere and I tell you which is the least separation, then it was a classical mathematician. Who was that? I don't know, the name won't come to my mind now, but something like in the 60s, it was proved that the maximum separation was a constant divided by a square root of n with a precise constant. Precise, very precise constant. It's not like 2. It's like a square root of 3 over 8 times pi or something like that. So known, the exact separation is known up to the first order, say. Constant over a square root of n with no constant, plus little order terms. But this does not help in solving the energy problem. Moreover, most people would say numerically that it is much easier to try to solve the log energy problem than to find collections of optimally separated points. Because optimally separated points, well, that's not even a smooth function. So it's quite harder to find them numerically. And people, what they would do actually is they would program points whose logarithmic energy or whose Riesz energy is small, and from there try to move them a bit to see if they get to the other. But there is no theoretical result about that. Even there is no theoretical result about problems that solve the Thomson potential, collections that solve the Thomson potential. Will they solve the logarithmic potential? Not known.
Thank you.
Thanks.
What if you want to find K roots?
Well, actually, this, from the point of view of theory, yeah, thank you very much, Mike, because that is actually a good point of what we got. Because from the point of view of theory, the results here up to here, all these results only find 1 0, 1 root. The most that we would have up to here with these randomized methods is that since we know that the probability of getting to any of the zeros is equal, then you can try it for k log k times, and most likely you will get to k different roots, right? So that's something that you can do, and only losing a log k factor. Now, after the results saying that a good, well-conditioned polynomial gives well-conditioned homotopy, well-behaved homotopy, then with this result of ours, we would get all the zeros of the polynomial. And this now proved in theory without this extra log k factor. Now it would be to be discussed if the log k factor is bad enough, and the answer is no, because still, since the other probability with the randomized systems is proved to be better complexity, even although you lose log k, you don't actually care, right? But yeah, so that would be the state of the art, I think.
Any more questions? Then let's thank again.
Thank you very much.
Okay, so let's start again. This is now the last morning talk, and it is by Didier Henrion, Inverse Kinematics with Computer Algebra and the Lasserre Hierarchy. Please.
Thank you. Thanks to the organizers for the invitation, the opportunity to speak in front of this diverse audience. So my background is in control theory, so I'm very interested in dynamical systems and their control. However, I decided not to speak about dynamics too much today, and I will focus on solving polynomial system equations. But I will not especially be interested in finding all solutions, but only an optimal solution with respect to some objective function. And so that's polynomial system equations that arises in robotics, the problem of inverse kinematics, which I will be introducing. And in order to solve the underlying optimization problem, I will use a blend of computer algebra techniques, Robner basis computations, and convex optimization, and the so-called Lasserre, also called moment sum of squares hierarchy, which relies on convex optimization and semi-definite optimization. So this will be a blend of techniques from applied mathematics. So the outline of the talk is the following. I'll start with the inverse kinematics problem. I will formulate it as a POP. POP stands for polynomial optimization problem. So it will be a problem of minimizing a certain polynomial over polynomial equations and polynomial inequalities. And this problem has kept us busy in Toulouse with my colleague Jean-Bernard Lasserre for the last 25 years. And we designed a technique which is now called the Lasserre hierarchy, or the moment sum of squares hierarchy, which I will talk about. And maybe if time allows, I will explain a little bit more in detail how it works, and which consists of solving the problem of a polynomial, the POP, at the price of solving a family of convex optimization problems, namely semi-definite optimization problem of increasing size. So we solve a non-convex problem over polynomials at the price of solving not a single convex optimization problem, but a family of convex optimization problems, hence the name hierarchy. So we'll show you how we can actually have troubles if we directly apply the Lasserre hierarchy on these inverse kinematic problems, and how we can use, in the third part of the talk, computer algebra techniques to reduce the POP in some sense, so that applying the Lasserre hierarchy on it is much more efficient. So there will be a reduction to the POP, which will allow us to solve the kinematics problem almost always. And then this will be illustrated by numerical experiments. So first, introduction to the inverse kinematics problem. So basically, it's not really a dynamical problem. It's a static problem. You want to find robot control parameters, bringing the robot, here it's a robotic arm, into a desired position under some constraints, under some physical constraints. So robots of interest typically have several degrees of freedom, and here is an example of a 6 degree of freedom robot. And this problem of inverse kinematics can be reduced to solving a system of equation. And if you have more than 6 degrees of freedom, actually this can be reduced to not solving a system equation, but minimizing a certain polynomial subject to polynomial constraints, what we called POP, polynomial optimization problem. So if we apply a forward kinematics equation from n to base, we have a series of matrix multiplications, and each matrix is 4 matrix depending on one angle. The angles are denoted thetas, and there are 7 of them for 7 degrees of freedom robots. This matrix corresponds to a combination of position and rotation. And the matrix is a trigonometric function of the angle theta I, for I ranging from 1 to 7. And the inverse kinematic problems consist of inverting this relation, namely the given matrix here on the left-hand side. The matrix here on the left-hand side is given. This is the desired robot position, and we want to find the angles that make the robot take this angle and this position and angle and rotation. So each angle is parameterized by its cosine Ci and sine Si. So eventually we end up with 12 equations, 12 polynomial equations of degree 7 in 14 variables. And in that form, it's a little bit too much for state-of-the-art methods for solving polynomial equations. However, we can easily reduce the degree to 4 just by rewriting the equation as follows, by inverting 4 of the matrices on the left and on the right. And so that we end up with constraints which are degree 4 polynomial constraints in 14 variables. And among all the solutions, there are infinitely many of them. We want one which minimizes some criterion. Here it's weighted relative position of the angles. It can be something else. That's just a choice among others. And on the top of that, we'll have physical constraints on the position of the robot, which translates into bound constraints on the angles. So the lower and upper bounds on each theta I are given. So that eventually we came up with a POP, polynomial optimization problem, where you can see here these degree 4 polynomial corresponding to the kinematics constraints, these matrices, matrix multiplications. And we have 14 variables corresponding to the cosines and the size of the angles to be found. And we have the objective function. So that's a priori not so easy problem to solve. And it's non-convex. However, we aim at solving it globally. We want the global minimum over 14 real variables. And for that, we can use this technique, the Lasserre hierarchy, which I will summarize very quickly with this slide. But as I said, I can tell you more about it later on, if time allows, and you're interested. So this is called also the moment sum of squares hierarchy, because it relies on the duality between the cone of positive polynomials and the cone of probability measure, the cone of measures and their moments. And we'll be approximating these cones with polynomial sum of squares. And the reason we use polynomial sum of squares is that deciding whether a polynomial can be written as a sum of squares boils down to semi-definite optimization, which is linear programming in the cone of non-negative quadratic functions. And for that, we have powerful numerical methods. The way we use this duality between these cones is that we reformulate the original polynomial optimization problem as a family of moment sum of squares semi-definite programs. And this family is indexed by its size or its relaxation order, capital R. And we solve this each problem in this family, each convex optimization problem in this family for increasing values of R until some condition is satisfied. And this condition is expressed as a rank condition on the solution, on the output of the solver. And if this rank condition is satisfied, we have a guarantee that we could solve the original non-convex POP at the price of solving semi-definite relaxation. Okay, and in 2002, some 20 years ago, we designed software which is called GloptiPoly, Global Optimization over Polynomials, that allows us to model these relaxations, these moment sum of squares relaxation for a given POP. So for this kinematics problem, we just tried, just took our software, input the problem, and looked at the solutions and whether we could certify global optimality. So this is some advertisement for the moment sum of squares hierarchy, a recent book we wrote with Jean-Bernard Lasserre and our colleague Milan Corda in Toulouse. And also there is an ongoing European project, which is called POEMA, Polynomial Optimization, Efficiency through Moments and Algebra, on these techniques. So if we apply the Lasserre hierarchy on this kinematics, inverse kinematics POP, we very quickly come up with difficulties in the sense that the size of the semi-definite relaxation, this convex problem, grows exponentially with the number of variables. So number of variables n here 14. So the growth is polynomial in the relaxation order. The number of variables in each convex optimization problem grows polynomially as a function of the relaxation order, but the exponent is the number of variables. So here it's 14, so it grows very quickly. And we observe that already at the third relaxation in the family, the problem is too large to be solved on a standard laptop. So we're, in principle, the problem could be solved if we would have a larger computer. But for this kinematics problem, we would be happy to have a solution on the small computer. And we observe that 14 variables is a little bit too much. And so we came up with a solution still of the problem, but it goes through a reduction of the original POP. So we'll use computer algebra technique to remodel the problem and to reduce the degree of the polynomial equations in the problem. And for that, we use computer algebra techniques. So it turns out that these degree 4 kinematic polynomials that I denoted pi in the POP, and the degree 2 trigonometric polynomial equations, actually, they can be replaced by only degree 2 polynomials. So we don't understand why this is the case. We don't understand the physics of it, but it turns out that we don't have to go to degree 4 in order to model the same problem. And the proof that the ideal generated by this degree 4 polynomial is actually the same as ideal generated by other degree 2 polynomials is computational. So we use a generic instance of manipulator and a pose, and we generate a Grobner basis of the ideal spanned by the polynomials. We generate a Grobner basis of the ideal generated by only taking degree 2 polynomials in the basis, and we prove computationally that these are the same ideals. So this can be done with computer algebra techniques, so operation over integer numbers. Here it is using Maple commands and Grobner basis engine. And it means that we don't have to go to degree 4 polynomials to model the inverse schematic pop, which means that we could apply the Lasserre hierarchy on this lower degree pop. And we validated this technique on a KUKA robotic arm, which is a rather well understood and well studied device. And for almost all instances, for almost all possible position, required position of the robotic arm, we could solve globally with this rank certificate, the reduced pop. Okay, so here is an idea of how the reduction affects the size of the problem, and the size of the reduced problem is much more manageable on a laptop like this one. So for the original pop, we had failure rate, meaning convex optimization problems that were too large to be solved, of the order of 1/3. And for the reduced pop, the failure rate was reduced to a little bit more than 1%. So we could solve the problem in most of the cases. So here the red dots correspond to configuration points for which we could not solve the pop. And here the green dots and the correspond to problems for which we could solve the prop and the robotic arm could generate this position. Whereas in blue, we could solve the pop, but we could also prove using duality that there is no solution to the pop, meaning that the equations were not consistent over the real numbers. So no solution. This we can do as well. So just an idea of the execution times. Okay. So you see it's a matter of a few seconds. And you see that this is the time required to model the problem using our package, and also to solve the semi-definite optimization problem. And this is the time used to generate this Grobner basis proof that degree 2 polynomials are enough to model the same problem. So you see that it's also by the order of a few seconds. Okay, so just as a summary, we could formulate this inverse kinematics problem as a degree 4 polynomial optimization problem. And since we are dealing with 14 variables, 7 degrees of freedom, this is a little bit too much for state-of-the-art numerical methods based on the Lasserre hierarchy. But we observed using computer algebra techniques that we could reduce the degree of the pop to 2 instead of 4. And the proof is computational, based on Grobner basis computations. And this allowed us to solve the inverse schematic problem in most of the instances. That's it. So this is a joint work with roboticists in Prague. And so Pavel Trutman and Tomáš Pajdla, they are experts in robotics in the Czech Technical University in Prague, in the Czech Republic. And this is also joint work with Moab Safeh Eldin in Paris at Sorbonne University, who is an expert in computer algebra. So if you're interested in knowing more, we have a publication on that. And there is also a GitHub repository by Pavel Trutman with all the codes available. So now I can pause. I can take a few of your questions. And if you are not tired enough, I can tell you more about the moment sum of squares hierarchy. Questions? Yes.
Have you tried to substitute to your 4x4 real matrix quaternion? Because sometimes when you use quaternions instead of matrix, the fast of
you mean here already at
your rotation at the beginning?
Here.
Maybe
at the very beginning here.
Yeah.
I see.
when you consider
to model each of these matrix action by quaternions.
Exactly.
I don't believe we tried that.
Because
but would that reduce somehow the problem?
You do only one multiplication instead of course, you have to implement the product over the quaternions.
Product of quaternions, yeah. Yeah. But then what would be the unknowns? The parameter in the... So you will still have the same number of unknowns?
Rotation in R4 are parameterized by quaternions. Is a different model.
Okay. Oh, yeah. Oh, yeah. No, we did not try that. Maybe this would also, lead to different polynomials. And
a quaternion number is like a complex number as a polar form.
Yes.
And so there is an angle corresponding to your theta.
Yes, I see. Yeah. No, we didn't try that. Yeah. This is something to investigate indeed. Thank you. Yeah.
Here's the question. How about the Lasserre hierarchy? In the problem, the family of SDB converts finitely steps on in the problem.
In this problem, yes, we have finite convergence, and but we are not able to prove that. For example, without reducing the problem, we are not able to prove that relaxation order 3 always solve the problem. I don't know if it's related to your question. You're asking about finite convergence.
Yes.
In general, or for this problem? In general.
In general, I know that the Lasserre hierarchy is finite.
Yes, for generic pop, it has finite convergence. Yes, generically, yes. Yeah.
But in the problem, how about in the problem?
So for this problem, we expect this relaxation order to solve, if not all, most of the problem. The issue is that the size of the relaxation is too large for a standard computer.
I see.
You see, so this is why we had to reduce the problem, and for the reduced problem, we could solve not for all, but almost all problems. So we still don't understand actually this little bit over 1% of problems for which either we have to go to the next relaxation order, or maybe something went wrong with the numerical solution of the semi-definite problem, and this we don't understand. So it's just that we are not able, in these cases, to produce a meaningful solution to the problem. Yeah. But we don't know how to prove, for example, that degree 3 order 3, sorry, always solves the problem. We don't know how to do that. Yeah.
And I know that in the Lasserre hierarchy, we can find the optimum value.
Yes.
But how about the solution optima?
What about what?
How about the optimal solution, not value?
The optimal, not the optimal value, but the optimal solutions. Yes. Okay, I did not mention that. From the solution of the semi-definite problem, we look at ranks of so-called moment matrices. And if the rank of these moment matrices stabilize, then the number of globally optimal solution is this rank. And from linear algebra computation, eigenvalue computation of this moment on these moment matrices, we can compute the solutions. And here we observe just that the solution is rank 1. So there is a single solution in all the cases. Yes. So rank 1, which means first degree moments. Yeah.
I see.
Yeah.
Okay. Thank you.
Yeah. So, yeah.
Yeah, can I have a couple of questions? So
Sure,
first, did you test your algorithm with other, like there's some famous, some well-known, okay, I don't know, well-known numerical methods in robotics, like KDL, IK, or IK fast solver. So,
Yeah.
so did you test with those?
No, we didn't. And you're right that actually for this particular robot, this KUKA robot, which I presented very briefly at the end, there are other techniques, mostly heuristics, that work very well to solve the inverse kinematic problems. So it's not really considered as an open problem in robotics to solve this inverse kinematics problem for this particular robot. So for us, this was just not a toy example, but say a sanity check that the Grobner basis reduction method worked well and produced reduced pop solving the problem. But even though we could publish that in robotics journal, we don't claim we could solve challenging inverse schematic problems for this particular robot. And there are other techniques to solve the same problem, which we did not compare with and did not investigate. And actually the robot itself, when you buy it from this, I think it's a German company, this KUKA, you have already the inverse kinematics algorithm implemented in the robot. So it's not, and the robot has been designed so that the inverse kinematic problems can be solved using heuristics quite well. So it's not considered as a really challenging test case for roboticists.
Okay.
Yes.
Thanks.
Yes. Yeah.
So second question, so you have a slide where you say you have some failure. So
yes.
what are the criteria for something to fail?
Yeah, well, failure means for us that okay, here there are the red dots, and here there are a few red dots that maybe you can't see, but I can see them if I come very close. These are this 1% of dots, which means that the relaxation, the semi-definite relaxation could be solved, but we could not observe this rank pattern in a moment matrix that would certify that the solution is globally optimal. It implies that we have to solve the next semi-definite problem in the hierarchy, but this one, again, would be too large on this kind of computer, on a laptop, to be solved. So this we consider to be a failure, you know.
Okay. And
so
then,
so the drawback with this hierarchy is that if you give me a polynomial optimization problem, unless its model is convex and it has very, very nice regularity properties, I will not be able to tell you how far you have to go in the relaxation order, how large must be the semi-definite problem, so that I can be sure I solve globally your problem. I have to try incrementally and look at these rank patterns. That's the only way, that's the only practical way we could find. Yeah. And we don't understand fully this. I mean, it may happen that there is a restricted class of pops for which we could have a uniform bound on the relaxation order R, but so far we don't have that. Even for much simpler problem, we are missing these guarantees. Yeah.
Okay, and so maybe my last question. So you have a table maybe at the end, something, and then you say that in some cases you have no solution, right? You have no solution.
Yes, these are these blue dots, which means that for this configuration of the robot there is no possibility to bring it to the desired position because of the constraints. You know, there are some physical configuration which are just impossible.
Yeah. So I mean that so I mean if you try to solve it correctly, so maybe you don't have solution, but maybe if you try to do it like iteratively, maybe you could find something, not a solution, but it's close to something optimal, right? Not solution.
I think that here in this case we have something which is much stronger in the sense that we have a certificate that there is no solution of the reals of these inequalities and equations. So this semi-algebraic set is empty, and we have a certificate of emptiness, and this goes to the workhouse of the moment sum of squares hierarchy, which is a so-called positive Chalansatz, which is a certificate of positivity using sum of squares. And this can be used to certify emptiness of a semi-algebraic real set as well.
Yeah, yeah,
you know?
yeah. I understand, but I mean that from a practical.
Yes.
Practical viewpoint. So even you want this both, and then
Yes.
you have no solution, but maybe you could try to find a solution to a nearby an approximation, right? And if you do like if you use iterative methods, maybe you could find that those kind of solution. But if you do this, then maybe you couldn't find, right?
If you relax these constraints, you may find a solution, yes.
Okay.
But if you enforce them, there is no solution. So it means that the physical constraints on your robot are too strong, and you cannot bring it to this position. There is a physical obstacle.
Yeah, I understand that. But I mean, well, you cannot do this, but well, you can do it close to it, something.
Yeah, but then it depends on how much you you allow this to be violated. If there are very strong physical constraints, there is no closed solution. It's just empty, period. You know, so it's really a matter of then engineering whether you allow some violation of the constraints or not.
Yeah, I think in practice they don't care, right? They just want a solution. Yeah.
No. In these blue dot cases, they want to know all these blue dots. You have certificate that it's not possible to bring the robot to this desired position. So it's just impossible, and engineers want to know that.
Okay.
You know, and you're even not close by. You don't get it.
Yeah. Okay. So
know?
maybe I give another maybe an analog, not this one, but maybe the same, similar. So you want to show us an equation in real numbers, right?
Okay.
And that may not have any solution, but if you use like iterative methods, you could find not a solution, but you find optimal solution, optimal value.
Okay.
So it's just what,
So it may happen indeed that for these blue dots, which are next to the green ones, you have an almost or epsilon solution that could be indeed interesting also for the engineers. Yeah, but for the ones which are far apart, that's really a physical impossibility. Yeah. So I still have time, but I don't want to spoil you too much of the lunch break. So if there are questions on the moment sum of squared hierarchy, I would be happy to address them. Otherwise, thank you for your attention.
Welcome in this afternoon session. The first talk will be given by Yurii Nesterov, and is entitled Quartic regularity.
Okay, thank you very much for inviting me at this interesting conference. Actually, for me, it is always interesting to be at the conferences where the pure mathematicians and applied mathematicians, they meet together and they can exchange their, let me say, achievements and their, let me say, positions and so on. And you see, actually, so both of us were mathematicians, which means that we are supposed to prove theorems about something, but the style of their work is completely different. So for the pure mathematicians, so they are challenged by very difficult and general questions, immortal questions, immortal theories. And applied mathematicians, it is a little bit different because we are very interested in the easy problems. You see, so the problems which we write just on the paper, so they are, of course, mathematically, they are correct. But I don't know why, but very often it appears that numerically they are unsolvable. If you look at problem of combinatorial optimization, yes, so almost all of them are in p-hard, which means that you cannot really address the problems of big size. At least we cannot give the guarantees that such problems can be solved. And for nonlinear optimization, the situation is even worse. So you have seen the previous lecture by Didier, where, I'm sorry, the toy problems with seven variables, so becomes unsolvable just by the modern approaches and so on. Therefore, we very much interested in finding, so among all these big set of unsolvable problems, to find problems which are still solvable and moreover the solvable efficiently, and to prove some theories around that. And today I'll show you something which is related to polynomials of degree 4. Okay, minimization problems related to the polynomial of degree 4, which are again in general, so form the class of NP-hard problems. So we cannot minimize the polynomial of degree 4 except the P is equal to NP, but still it appears that in this big family of unsolvable problems, we can find a subclass of problems which is quite solvable and which is useful for many practical applications. So this is the goal of my talk. And the reason for this advance is actually convexity. So convexity was not mentioned at our conference at this moment at all, but for optimization, it is extremely important. It is exactly what gives us the class of solvable problems. And from the viewpoint of modeling, so it is a very easy and understandable thing. So if we have two variants of the solution, then all intermediate variants are also feasible. Yeah, this is convexity. And if we have the problems of that type, so then we have solvability, numerical solvability. Of course, the question is how much it is related to polynomials, minimization of polynomials, because clearly polynomials is very non-linear. So, and some polynomials clearly cannot be convex, like polynomials of degree 3. Okay, but we will see. So what do we have? And for people which are not specialists in optimization, I just give you some, let me say, historical remarks, some motivation of these results. So from the viewpoint of optimization point of view, and all of that actually started somewhere 15 years ago when we managed to develop the cubic regularization of the Newton scheme. So Newton scheme has already mentioned at this conference several times. So, and always, so when we speak about Newton method, so we speak about local quadratic convergence of this scheme. So when our problem is non-degenerate, so everybody knows that we have local quadratic convergence. Yeah, yeah. But what about global convergence? You know, so when we analyze numerical methods, okay, so usually we start from some starting point, and very often it is very far from our optimal solution. So we need to come close to the solution, and then so we can expect the very fast quadratic convergence. But note that theoretical analysis of quadratic convergence is not very interesting. So each iteration of the method, so if we have quadratic convergence, it doubles the number of right digits, which means that how many iterations we can have after the beginning of quadratic convergence. Clearly, so it is maybe 3, 4, 5, something, I don't know, constant. Yes. Therefore, the main work, the main computational efforts in all these schemes are spent at the first period, first phase of this process, when we are trying to get to come from the initial point to the region of the quadratic convergence. And during decades, actually, so this complexity was not addressed at all. And only 15 years ago, we managed to do something in this direction using so-called cubic regularization of the Newton scheme, where we considered the methods where the second order approximation, local approximation of our objective function was augmented by the cubic penalty form. Okay, the cube of Euclidean norm, and at each iteration, so it was necessary to minimize this construction. And then, so it was possible to write down the global rate of convergence of the process, to analyze that. Now, so I'm not sure that I can write on the blackboard. I can, but I'm allowed. No, because the people, oh, there's nobody. Okay, anyway, yeah, so. Yeah, I can, yes. Yes. So the complexity, global complexity of the estimates. So we want to minimize function in X. Suppose there is no constraints. Then we want to find the point X bar such the residual between this point and the optimal point is smaller than epsilon. And the question is how many iterations of our scheme so we need in order to find this stuff. So in order to do that, so we need to assume that the function is convex, which means that the Hessian is a positive semi-definite matrix, and also the usual condition, which is standard for the local convergence, is the Lipschitz continuity of the second derivative. Okay, this is Lipschitz condition of the second derivative. So under this assumption, so we can write down the global convergence for the Newton scheme in this sense that Fk, f at xk minus f star or decreases like that, divided by k squared, where k is the number of iterations. This is the global complexity bounds from which, so if we say that the right-hand side is smaller than epsilon, we can easily find the number of iterations which we need in order to come here. And if we look actually at this estimate, it was really a big surprise for us. So we immediately see that now we are in a situation where the standard complexity theory for optimization problems simply doesn't work. Why it doesn't work? Because the usual, let me say, efficiency bounds for in optimization were always written in terms of so-called condition number. Condition number, we have already seen it today several times. So condition number. So in optimization, what is it? This is the asphericity of the level set. So we take the level set f of x less or equal f of x 0. So this is something like that. We put the ball inside, okay, and we put the ball outside, and the ratio between these two numbers, so it's called the condition number of the problem. Very classical, I don't know, definition of the condition number for a function which exists during 50 years maybe, and it is immediately clear that in our situation it doesn't work. So the complexity of the second order schemes doesn't depend on this condition number. Why? Just because we can add to our objective function any quadratic function, yes, like this, the squared linear form with the big coefficients. And if we look at the Lipschitz condition for our Hessian, they see that it is, so the Lipschitz constant is not changing. Whatever we add to our function, quadratic function, so it is eliminated by the Newton scheme by one step. But of course, so by adding this guy, we can make the condition number of our function as bad as we want. So which means that the standard condition number cannot be used for analyzing the second order schemes. And consequently, so, and this is a confirmation that the standard optimization theory was basically created for the first order methods. For second order schemes, it doesn't work. And also, and it also, of course, doesn't work for the higher order schemes. So this was our next step. So we were trying to understand how we can analyze and in which terms we can describe complexity of the problems for the higher order methods. What are higher order methods? So they are methods which are based not only on the quadratic approximation of our function, but on the approximation of the higher order. Again, so I'm personally interested in the methods which are the most efficient in practice, and therefore we never looked at this guy, because the high order methods for people in numerics, it is just a nightmare. Just imagine that you need to program all these partial derivatives and fill, I don't know, this tensor, which has dimension, so matrix has dimension n square. So it is already a lot. But if we look at the third order, the tensor, it is n cube, n4, and so on. So absolutely impossible imagine that anybody wants to do that on one thing. And on the other thing, so how we implement one iterations of this guy. Yes, so with the Newton method, of course, it is simple. So we need to solve the system of linear equation. But if we speak about the higher order method, starting from the third order method and so on, it's absolutely not clear how we can solve it. And of course, again, from the general philosophy, so we should work with methods, only with methods for which each iteration is implementable, which means that auxiliary problem at each iteration must be convex. Is it possible to do that for the higher order method? And this is exactly our main observation at that time. So it was proved. And actually, it is a very simple fact. Strangely enough, people didn't look at that before, that if our initial function is convex, then, and its derivative of the order p is Lipschitz continuous, then we can look at its Taylor polynomial, add a regularization term like norm to the power p plus 1, and we get a convex function. So the trick is not evident at all, because people in optimization know that we cannot make the problem convex using addition of the high power. It is just impossible. Usually it is just impossible. Look what happens. Look what happens in one dimension if we add to non-convex function x to the power 3, yes? So the regularizer x to the power 4 with arbitrary big coefficient, positive coefficient m. No, you never eliminate non-convexity in the neighborhood of 0. It will be always non-convex. But it appears that if our Taylor polynomial, for example, the Taylor polynomial of degree 3 corresponds to the convex function, then this regularization works, and we have a regular source of generating the convex polynomial of any degree. The thing which was absent in this field during all the time, because in general, if you get a polynomial from somebody from outside and you don't know anything about it, in order to prove convexity of this polynomial, so it isn't a hard problem, it is impossible. But if we know that this polynomial is a Taylor polynomial for of convex function, then it appears that everything is okay. So we can be sure that the result is convex, and this means that we can use this construction, Taylor polynomial plus regularizer, at each iteration of our high order optimization scheme. So therefore, I would like to see how globty poly can do that. So very nice. And so, and therefore we can consider now the high order method. So at each we have the auxiliary problem as minimizing Taylor polynomial plus an appropriate regularizer in order to have the convex auxiliary problem. Okay. Now, here, actually, the situation is even better, because in order to apply this operation, in principle, we even don't need to compute the whole tensor. So, and we will discuss this a little bit later, but just directional derivatives are needed. Therefore, these schemes are absolutely fully implementable and can be used in practice. In some sense, so this is the topic of my talk, how to do that. Now, but of course, the main question is how to solve the auxiliary problem. Yeah, so the auxiliary problem now is quite difficult. So it is a multi-dimensional polynomial of certain degree. Yes, so degree p, in fact, we can choose the degree now arbitrarily. So we regularize it, we get convex function, but how to solve that? So unfortunately, again, so as far as I know, so we do not, from the general theory of algebraic geometry, we don't know how to solve this problem efficiently. But we can do in this direction just the first step. So instead of the second order methods, consider the third order methods. The third order methods where then here p is equal to 3. So we need to minimize the Taylor polynomial of degree 3 plus the Euclidean norm to the power 4. And it appears that this auxiliary problem so can be solved efficiently by the second order scheme. So, and this is more or less corresponds to the topic of my talk, because now our goal, I'm not sure that you can see. No? Can you see the last line? Yeah, our goal is to study this problem class, the problem class, which is now the convex polynomial of degree 4. So what are the methods for solving convex polynomials of degree 4? This is a goal. So before we discuss that, let me introduce some notation related to the derivatives, high order derivatives of function of several variables. Okay, so first of all, the directional derivative. We have a function phi of n variables. Actually, E is finite dimensional real vector space. Okay, and using this function, so it is differentiable many times as much as we want. So we can consider the directional derivative of degree p. Okay, so which means that we differentiate it along p directions, h1, hp, and with very mild assumptions. So we get a symmetric p-linear form. So this is the notation. Now, so just a short notation, if all directions are the same, okay, so we use then the dp along the h to the power p. This is just directional derivative of degree p of our function phi. Now, how it is related to four linear forms. So since we are speaking about the polynomial of degree 4, so for us, it is just the maximal derivative which we use. So it is convenient to relate to describe the behavior of this three linear form using this in terms of this function phi. Yeah, so we take all directions the same. So then we have the polynomial of degree 4 of n variables. And then, so if we look at the gradient, the usual gradient of this function, then it is related to the value of this four linear form on 3 vectors in this way. It is just the gradient of function. So the form along 2 directions gives us the Hessian of our function, and so on. Yes, so the form of along single direction for linear form, it gives us the third derivative, and actually the fourth derivative corresponds just to our tensor f. So it is just in order to understand so relation between the derivatives and the value of the forms. Now, what we are going to do now, so we consider the optimization problem. Okay, the optimization problem where you have the objective function f and the additive term psi. Actually, for people which are not familiar with this composite optimization form, so can think that psi is just identically equal to 0, but for others, so it is just the composite optimization problems, and psi is a simple function like indicator function or very simple function, so which allows us solution of the auxiliary problem. So this is the modern and convenient form of optimization problem. For us, it is important. So what is the function f here? Yes, so f at this moment is just a convex polynomial of degree 4. Convex polynomial of degree 4. Therefore, its Taylor expansion at any point, let us write it down, so we can, is finite. Okay, so it is exact. Yes, and it is composed by the gradient, the second order term, the third order term, and finally the value of our fourth derivative, which is constant. It doesn't depend on x, since so our polynomial is of degree 4. Okay. Now, so we know that our polynomial is convex. Okay, so at this moment, so we can prove it by the origin, for example, of our polynomial. But what happens with this four linear form? Because in our polynomial, we also have linear function, quadratic function, third derivatives, but this guy. So what happens with this guy? So it appears that this four linear form, so is also convex function. So we can see that since its second derivative along two vectors, so is greater or equal to 0, which means that the Hessian of this four linear form is positive semi-definite. So I just show you the proof just in one line. So we represent the second derivative using the Taylor expansion, for example, at 0. So the representation is exact since this is a polynomial of degree 4. And now we multiply it 2 times by the vector h and see what happens from in the right hand side. Yes. So the left hand side, since our function is convex, is greater or equal to 0. And here you see that we have different degree of homogeneity in y. Therefore, we can multiply y by some positive coefficient and take the limit when tau goes to infinity, which gives us the possibility of the quadratic positivity of the quadratic term. Yeah. So this again. So if we take the convex for polynomial degree 4, so its fourth derivative is a convex function. Now, there are some consequences which maybe I don't know, maybe it is not necessary to discuss in details. So just, so this four linear form, F4, yes, so it appears it has some properties which are very familiar to the properties of the norm. And this is actually exactly what we're going to do now. Yeah, so now our assumption at this moment is that the fourth derivative of our function is positive definite. And this means that this four linear form can define the norm. Yeah, so from this inequality, we know that this will be indeed the norm, which describes well our objective function. Again, in our objective function, we do have not only this form for linear form, but also other things. But it appears that altogether they work very well. So at least there are several nice properties. So about the growth of our function of this guy with respect to the linear approximation. So it appears that we get in optimization, it is called uniform convexity of degree 4. So also the interesting property is that so this function d, again, d is the polynomial of degree 4, so grows at least quadratically with respect to any point x. For optimization, actually, all these things are important. And also, the interesting thing that we take a square root of this this function for linear form. So we get, strangely enough, we get a function with Lipschitz continuous gradient. So it will be homogeneous function of degree 2, but it will have Lipschitz continuous gradients. Anyway, so for optimization, all these properties are important. But now let us look how we can minimize this convex quartic polynomial. Yeah. So the main thing, and actually this is the general thing, and this is really the basic reason of all our possibilities. So it appears that if we have convex quartic polynomial, then its derivative is always weak with respect to the second derivative and the fourth derivative. Third derivative can be always majorated by the combination of these two guys. And this means that in some sense, we can throw it out from our construction and consider methods which are basically, we are using the second derivative and an upper approximation for the fourth derivative. So this is, fact is indeed just trivial. Very simple. So therefore, I give you the proof. Yes, so we take the Hessian of our convex quartic polynomial at the point x minus tau h. Tau is a step size, h is a direction. So since the polynomial is of degree 4, so this second order derivative can be represented in this way. Since so we have convex function, this is greater or equal to 0. And now, so we just drop this guy, put third derivative in the left-hand side and divide by tau. You see that we get our inequality, so in this form. And this is the reason why we can do many things with even with the second approximation, assuming at this moment that our fourth our form for 4, yes, so the fourth derivative of our initial function is simple. So this is not very bad assumption, I mean, so we know, for example, for the third order method, so we'll see that. So this is exactly the case. So yeah, so when we regularize the cubic Taylor polynomial by the power of Euclidean norm, so the fourth derivative is simple. It is just the fourth power of Euclidean norm. So let us look, so what we can do then. Yeah, it appears that using this inequality for the derivative, we can write down for our function, so the lower and upper bound. So what is this actually here? This is a construction which we get from the exact Taylor expansion by replacing the third derivative there by its bound, this bound. In this case, from below, we just replace h by minus h, and we have lower bound for the third derivative. Lower bound for the third derivative gives us lower bound for the function, and it appears it has this form. So what is it? First, the beginning is very clear. So this is a modified second order approximation with certain term, but also we have this this term of degree 4. Yeah, again, it corresponds to our norm, which is related to this fourth derivative, which we assume to be simple. Now, let us look when this lower bound for our function is useful. So let us look at this coefficient. Tau is just guy which we have here. Yes, you see that in order to have the coefficient there positive, we need to have tau bigger than 1/3. And in order to have this guy useful, we need to have tau smaller than 1/2. So there is very tiny interval of useful coefficients, but still it exists. And we can mix so these things all together in order to have the lower bound for our objective function. And if we estimate the third derivative from the above, so we can do the same trick for the upper bound. The coefficients are changing, but in principle, it is also a thing with which we can work. Yeah. Now, again, in optimization, this is for global methods of global optimization. This is indeed the very general recipe. So if we want to minimize our function, so then we staying at some point x, we need to find an upper approximation, global upper approximation for our function and minimize it. Yes, so minimizing this global upper approximation gives us the improvement of our the function value. This is exactly what we are going to use to do now. So we have this f hat, yes, so which gives us the upper approximation of our objective function. So it is exact at the point x. If y is equal to x, all these guys equal to 0, and it has the good first derivative. It is tangent to the graph. Of course, the coefficients for the second order scheme is bigger. Yes, but not too much. Anyway, so this is exactly what we are going to analyze now. So it is called damped Quartic Newton method. So damped just because we have this coefficient here, which is different from 1/2. And this means that the steps size will be somehow a little bit small. Let us look at it. Yes, this is it. Yeah. So we choose tau in the interval from 1/3, 1/2. We minimize this upper approximation. Again, forget about this psi, it is 0, and see what happens. And it appears, since we have these two upper and lower approximations, which are very similar actually, so they composed by the same terms. So it is very easy to prove the global rate of convergence. What is it? It is linear. So the difference in the function value decreases as the geometric series, so with this coefficient alpha, where alpha, okay, so we can play a little bit with the numbers and get these terrible numbers. But finally, so alpha, so if we choose tau star here equal to that, yes, so you can check, so it is between 1/2 and 1/3, then we have linear rate of convergence. And this is actually the great victory, because if you look at the numerical analysis, there are not too many algorithms for which we have linear rate of convergence, which doesn't depend on anything. If you think so, this is maybe bisection in one dimension or whatever. Here we have multi-dimensional process which converge with the rate which doesn't depend on anything, any condition number, dimension, or whatever. So it is just like the very simple convergence rate. And this is for thing which is completely implementable using the standard technique of linear algebra. Yeah. So where we can use this? So this is what we have already mentioned several times. So if we have function f with Lipschitz continuous third derivative, then of course it is exactly the framework which we need to apply. And there, so at each iteration, we need to minimize the Taylor polynomial, which is of course non-convex. This is a polynomial of degree 3, it is never convex, but we augment it by the fourth power and we get the convex polynomial of degree 4 with simple fourth order term. So this guy, exactly what we just discussed now, and therefore, so all this stuff can be applied for finding the next point in our process. Yeah, yes, very simple second order scheme. I'll speak a little bit about implementation detail of this thing later. Okay, so what was our assumption here? So it was that we have fourth order polynomial with simple fourth derivative, yes, like here. So, but what happens? So let us make the next step. What happens if so the fourth order term is not simple? Then, as usual, so we can, if our fourth order term, so this norm is not simple, we can try to approximate it by a simple norm, which means that we can introduce another norm. So all norms in finite dimensional space, they're equivalent. So we can always, for any norm, can introduce this value, lower and upper bound, yes, in order to approximate our fourth order term there by some simple norm. And after that, so we can also repeat actually the things which we do before. So we need to find the approximations. So I'll just show you what do we get there, the lower approximation, the upper approximation. The difference with the previous approximation is that now, so we put here these coefficients, mu for the lower approximation and L for the upper approximation, but structure is exactly the same. Yeah, so now we get a kind of condition number. So this is the ratio between mu and L, which before was equal to 1. But in principle, so this is the same thing. Therefore, no problem with analyzing so-called relaxed Quartic Newton method. What is it? So now we use this upper approximation in this process, which depends on this constant L and which depends on the coefficient tau, which we need to choose properly. So what is it? Okay, so this is phi hat at the point xk and with the parameter tau. And it is not surprising that we are able to prove for this guy also the linear rate of convergence. Linear rate of convergence with this coefficient alpha, which must be strictly positive. Yeah. So let us look if it is possible or not. So that if tau is equal to 1/3, then this guy is 0, but this guy is strictly positive, which means that we can increase a little bit tau above 1/3, and we get positive right-hand side, and therefore we can choose this alpha strictly positive. Yeah, so, and we can even try to play with this right-hand side in order to see what happens with the optimal choice of tau. Of course, the optimal choice of tau just maximizes this constant. Yes, and it appears that it is close to this. So, and if we denote by kappa this condition number, Q is the ratio of mu and L in the power 1/3. So then this alpha is proportional to kappa somehow. Yes, so this means that the number iteration is proportional to 1/3 power of our condition number. Okay, fine. So this is, and note that this choice is not too much worse than our previous choice when Q was equal to 1, because here when we have good norm, so which means that the Q is equal to 1, we still have very reasonable lower bound for this coefficient alpha. Now, what happens now? So if the situation is even more complicated. Yeah, so all of that, so what we were speaking before was about the polynomial of degree 4, which means that our fourth order derivative is constant. But of course, so it is interesting to look at the problems where the fourth order derivative is changing. Can we apply our philosophy, if you want, to this more difficult situation? And indeed, so we can suggest the notion which is called Quartic regularity. Yeah? Quartic regularity. What is it? So again, so we look at the composite optimization problem again. So people which don't know optimization forget about this psi. So we have a function f, so which satisfies the assumption of Quartic regularity. What is it? It is very similar, by the way, to the notion of strong convexity, but already on another level. We assume that our second derivative is uniformly positive semi-definite. Okay. Uniformly positive semi-definite. Note that strong convexity corresponds to positive semi-definiteness of the second derivative. So if you think, so which derivatives we can assume to be positive semi-definite, so we immediately see that for third derivative, this is impossible. Third derivative cannot be semi-definite. It changes sign when we change the direction, multiply by direction by -1. But fourth derivative, it can be positive semi-definite. And it appears that this property so is indeed very useful for optimization methods. So actually, we just repeat more or less the same things which we did before, but already in the more difficult situation. So the second assumption that the fourth derivative is uniformly bounded is more or less standard. It corresponds to the Lipschitz continuity, global Lipschitz continuity of the third derivative and so on. But this guy is new. Now, let us look what we can prove for that again. So I don't want to discuss now. So we should speak a little bit about the domain and all things like that, but all of that is not very important. Yeah, so this is notion is actually more or less natural. So it so we can add such functions and see what happens with these parameters. We can put inside the non-degenerate affine transformations and so on. So this is more or less reasonable class of function. But for optimization, again, so it is very important. So what geometric inequalities we can have for this class of function. And it appears that even in this, even for this more complicated object, so we have still non-trivial lower bound. Again, with upper bound, there is no problem. So it is it comes from the standard inequalities. But what about the lower bound? Yes, so in the lower bound, so we have as usual the linear term. Now, the quadratic term, which corresponds to the second order approximation, but with coefficients which is smaller than 1/2. And this is now the long and difficult multiplier for the fourth order term. But this is indeed very important. This is exactly tells us what we can do with this thing. Let us look what we have here. We have this power 4 with coefficient mu and very strange coefficient. So this, yeah, where we have the term which is for us, playing for us, and this guy is playing against us. But gamma is between 1/3 and 1/2, and when gamma is equal to 1/3, so it disappears. And we have just absolute constants here, which means that we can increase a little bit gamma above 1/3 and still have here the positive multiplier, which means that again, so we have this global lower bound for our function, and we can prove the global global complexity bounds. So what is it? So the method is exactly the same. So we form the upper approximation of our function as before. So replacing the third derivative by the combination of the second and the fourth derivative. And at each iteration, so we minimize it and we get the new iterations. Huh? Yes, and but the important thing is what we can prove. So what is the rate of convergence? Oop. Yeah. Shit. The most important thing I am not sure that you will have here. So the last line tells us that we have linear rate with coefficients 1 minus alpha, where alpha finally, yeah, but still. Okay, where alpha, let me write down. So what is in the last line? And this is same as before. F of k minus f star less or equal 1 minus alpha to the power k, f of x0 minus f star. Okay, this is the main statement. Yeah. So the important thing, what is alpha? And you see, so the structure is exactly the same as before. So here we have this condition number, yes, and also this kappa of gamma. But anyway, so the coefficients are chosen in the way that this kappa of gamma is constant. So everything is more or less the same as before, and we get the linear rate of convergence. So where the coefficient is proportional to the root of the power 1 of the 3 of the condition number of our function, condition number of order 4, yes, so which gives us the bounds for the fourth derivative. So this result that has several interesting applications, but actually I just want to show you one of them. But wait a minute, sorry. So this is first the implementation details. Yeah, so the choice of the parameter. So in the previous scheme, so we need to choose this coefficient gamma in order to have this alpha good enough. So then this can be done quite easily. So there is just the direct formula which tells us that this alpha star, so which we put in this rate of convergence, is proportional to the root 1 over 3 of this condition number of our function. And therefore, in order to get epsilon solution, of course, we need the number of iterations proportional to 1 of root of the condition number, third root of the condition number, multiplied by logarithm of 1 over epsilon. Epsilon is the accuracy in the function value. Now, implementation. So here I tell you several times that actually we get the second order scheme, but actually in the second order scheme, usually we minimize the quadratic function. Here we minimize the quadratic function plus the function of degree 4. So how we can do that? And the standard trick is that we represent this fourth power of the displacement using the quadratic function. So look what we can do. Yeah, so this guy needs to be minimized. Therefore, we can represent this guy, this power 4, using the maximization problem. Yeah, so what is it? We do this. Y minus x to the power 4 is the maximum in R. Yes, this quadratic 4 multiplied by R minus R squared. Yeah, so this is just a simple computation. Now we need to minimize this guy xi hat plus this guy where we have maximum. Therefore, we can change max and min. Then inside of min, we will have only the quadratic function in y. So we'll have the usual quadratic minimization. We do that. Okay, and the result will be the function of R, one-dimensional function, which we can easily do this one-dimensional minimization. So therefore, again, so the scheme which we get, so is the second order scheme. Now, the main application, so last minutes, actually, maybe one of the most interesting applications of this stuff are in so-called high order proximal points methods. In optimization, so there is a famous construction of the proximal point operator when we take a prox tangent x bar and we add the norm of the difference between x and x bar in the power 2 to the objective function, and we minimize it, so-called Moreau-Yoshida regularization. This is absolutely classical stuff from 50s and 60s. But in the recent years, so it was shown that actually it is more interesting to replace here the power 2 by a higher power. Yes, higher power. So 3, 4, or whatever you want. And then increasing this power, we get more and more efficient algorithms. But of course, you pay for that by complexity of this proximal point operator. But now look what happens actually here. So if we look at the fourth derivative of our function f, so we just artificially increase it by this constant h. So which means that for this function, if we look at the bounds on the fourth derivatives, So the mu, coefficient mu, the lower bound can be taken h minus m4. M4 is the upper bound to the fourth derivative of this function. And the upper bound is h plus m4, which means that if we take h equal, for example, to 2m4, so we get the auxiliary problem with the condition number 1/3. And again, so we will have linear rate of convergence for this auxiliary operation. So again, everything is completely implementable. And these already the operations which can be easily inserted in different high-level optimization schemes. So for them, it will be low-level operations. And then, so now there is quite developed theory which tells us that you can have different methods with different rate of convergence, 1 over k cube, 1 over k4, 1 over k5, k is the number of iterations. So the last one especially interesting. You can play with the number. For example, 10 iterations gives you already 10 to the minus 5 accuracy, which is not bad at all. And this is the iteration which more or less corresponds to the complexity of the second order scheme. So therefore, this is an interesting direction for optimization, but for me, it is also justification that we have a new class of problems which was never considered seriously before. I mean, the problems of minimizing convex polynomials. What are the efficient methods for minimizing convex polynomials? And it was not considered just because we didn't have any regular source for generating this convex polynomial. Now we have one very important source, and it is interesting to see what kind of technique we can develop in these directions. Okay, this is all. Thank you.
Thanks, the speaker. We have time for a few questions.
Yeah.
The main lemma in the beginning, you have.
You remember the slide number?
I cannot see.
Oh,
sorry. In the beginning, you have no.
This is lemma 2.
No.
Lemma 1.
The main lemma. Yes.
Okay.
This.
Yes.
So in this case, did you assume that f is convex or not?
Function f is convex. From the convexity of function f, we derive the convexity of the fourth derivative.
Yes. And f is bounded from below or not?
F is what?
Bounded from below.
Doesn't matter actually.
Convex?
Not necessarily. So not, because you see, so at this moment, do not say anything. So this guy can be positive semi-definite, which means that there could be directions where this form is equal to 0. It is possible. And since we have linear terms, so along this direction, linear term can go up to minus infinity and so on. But still, so we have the convexity of the fourth derivative.
But I think that without assumption convexity of f, but f is bounded from below, so the main lemma is true.
No, because it can be that this guy is equal to 0 along y.
But f is bounded from below.
F not, no.
Okay.
F4 is bounded from below, yes, but F not.
But in the next the next slide, you have
this is assumption.
That's the first assumption. So this assumption and f is a polynomial of degree 4.
Yes.
So this assumption implies that f is bounded from below.
Yes.
And
from
f
this assumption, yes.
Yeah.
From this,
f is a cohesive. Yes.
Yes.
But yes.
From this assumption, yes, it follows. From the previous slide, no.
Yes.
Okay.
And this assumption equivalent to condition. The next slide, I don't remember this.
I don't.
After you have a condition
Here, no.
No, no.
Here,
After this slide.
Before this slide.
After.
Before next slide.
Next.
After, yeah, sorry. No, it is method already.
No. You have a no. The next.
you can maybe find yourself.
Okay. You have a condition number.
A condition number, yes. This is later. This is later. Of course, this is first for the simple guy, and after that.
Yes.
Yes.
This I think that this condition equivalent to.
It is equivalent to that. Yes, of course, because we are working with finite dimensions, so all norms are equivalent. So
okay, thank you.
Okay.
Thank you for a very nice talk. So I have just a few questions. So first one, this condition number.
Yeah.
Is it related to for example, if a function is strongly convex, is it satisfy this condition condition?
Second order derivative has no influence. So you see, we are speaking about the fourth order.
Yeah,
derivative.
I know that.
Second derivative disappears.
Yeah. So second derivative disappear? What?
Yeah. So in the fourth derivative, there is no second derivative. It is only the second.
Yeah, so I understand that. So we have now a new method that converse linear for converse linearly if it satisfies that condition, the condition with mu and L, right?
Yes.
So my question is if the objective function is convex and has a Lipschitz derivative and so on, it's strongly convex and has Lipschitz derivative, is it satisfy this condition?
I'm not sure actually. So I don't know. So this is a new class, and I don't know. So there are functions. There are examples of such functions. Yes. So clear example of such function. For example, if you have the summation of function of one variables which are computed linear form, so you can look at fourth derivative and see what happens actually. So there are functions of this type. Also, you can regularize. You can regularize in the way which I showed at the last slide.
Yeah, I can understand that this class of function is rather than the strongly convex function.
It is different.
Yeah, it's different. So my question is the strongly convex function is a subset of this one or not?
No.
Because for a strongly convex function, we can have first order method with linear convergent rate as well, right?
Yes,
maybe the rate method.
Yes. So no, this is a different class actually. This is a different class, and I think in some sense it is better than the class of strongly convex function. So now I just want to go to the last slide. So it appears that the standard theory of convex optimization, it works well for the first order methods.
Yeah.
Strong convexity and Lipschitz continuity of the gradient. This is a feature which are important for the first order methods.
Yeah.
For the second order methods, so it appears it is different, and it is even a situation even more interesting because from all these results we see that actually we don't need the third order methods.
Yes.
Everything which can be proved for the third order method can be done with the second order methods. You see, now there is no any more one-to-one correspondence between the method, order of the method, and the class of the function. Before it was like that. So first order method function with Lipschitz continuous gradient, second order methods function with Lipschitz continuous Hessian, third order methods Lipschitz continuous third derivative, and all things like that. Yes. Now, no. Second order scheme cover two classes at least. Second Lipschitz continuous Hessian and Lipschitz continuous third derivative. Yeah, and it is very interesting to see how much we can go, what is the next. But for that, so the first thing to do is to find so how we can minimize this contraction efficiently, convex polynomial. So the next will be the polynomial of degree 5. Yes, plus the Euclidean power to the power 6. So this is the next challenge.
Yeah. Thank you for the answer. My next question regarding to the coupling Newton method at the beginning. So you wrote on the board that the complexity is 1 over k square, right?
Yeah.
And this is not better than your accelerated Nesterov.
It can be accelerated. So I just write you as example. The important thing here was this coefficient L2.
Yeah.
And here actually you can have k to the power 3, k to the power 3.5, and so on. So you can have different strategies. But the important thing is this, because this guy is not changing when we add the quadratic
so it's
form.
not depend on the condition number.
Yes.
That's okay.
It doesn't depend on the condition number. Condition number for the second order schemes must be introduced differently. It is not the condition number for the first order scheme.
Okay, I got it. Yeah, thank you very much.
Okay.
Maybe your last question? Yes?
Yeah, I have several questions, but maybe I just ask you one question for now, and then maybe later.
Yeah, of course.
So just about the implementation. So you repeated that your method can be implemented. So do you have a kind of a code, or did you write some codes?
No. Well, we didn't implement it yet, actually, because now, well, there are different development. Actually, the problem is that we still are not sure. So, what is the best framework? So you see, So on one hand, so it can be implemented for this high order proximal order methods. On other hand, so it can be implemented to the usual third order methods. Yeah, so the same thing. So instead of that, at each iteration, we minimize the Taylor approximation. Or this one. So now, and actually we have more suggestions. So now we are somehow expanding, and of course we are going to do the numerical experiments.
I asked this because of two relevant things. So first, you have a theorem, right? But your theorem depends on this auxiliary truth return method that you need to do sub minimum question, and then you have theorem. So my question is, because when you implement, then usually you don't have a correct correct solution to your, but just maybe approximate. And then my question is, if you only have correct approximate solution, there's a fact that you could still prove your theorem, or you don't?
Usually, yes, no problem with that, because actually in order to prove the convergence, so you need to satisfy some condition. So usually it is condition which relates the improvement of your function with the norm of the gradient or something like that. And if this is satisfied, then everything is okay. And this you can check actually. This condition you can check. So very often there is no problem with that.
Okay, and then just one other relevant things. So you have the cubic Newton method, and then I tried to find a good implementation, but I couldn't find. I found some, but when I tried to test on iterations, so they don't do very well. Yeah, so
it is very important so to have in all these schemes so the right strategy for updating this H, the prox coefficient. Yes, if you do that in the conservative way, so the methods are not good, so they do not work. But you need to give it possibility to lift and to go down, so dependently on your current situation and so on. And then actually you indeed have have much more powerful schemes which are better than things which exist. So if you compare, for example, with trust region or whatever methods, so they simply do not work properly. And also, so in our last experiments, actually, not with exactly with these schemes, but with the adaptation of this constant, we see that we are doing better even than the first order methods. Not in the number of iterations, the number of iterations that is more or less natural. These methods are more powerful, but just in time. Okay, so the time we spend for auxiliary problems makes the efficiency much higher.
So you mean for convex problems, right?
For convex problems, yes.
Okay.
For non-convex, I don't know. Non-convex, of course, so this is completely different situation. And again, so look, so what it is different from the things which we was discussed in our first talk today when we were looking for number of roots and so on. So here, this is a very specific situation. So we have a polynomial which has single real root, and we're interested in finding it, not all roots and so on, just single real roots. And this is why all of that is very efficient.
Okay, thank you. Yeah.
Thanks.
Thanks, the speaker again.